All right, so today we're diving into some pretty serious math, I'd say. We're going to be exploring the world of parametrized functor calculus. I know you're all familiar with this area, so we can jump right in. And our source material today is a research paper titled Parametrized Functor Calculus, Excision, Spheres, and Semiadditivity. And it's by Kaif, Hilman, and Linskens. And it was just published on October 30th, 2024. So it's very recent. What really caught my eye about this paper is, it's tackling a pretty deep problem in homotopy theory. And it's making some really interesting connections to how mathematicians think about spheres and this concept of semiadditivity.
Right, yeah.
Which we'll get to, of course.
Yeah.
So our mission today is to really try to understand how Hilman and Linskens are generalizing Goodwillie's functor calculus to the broader parameterized setting. And then we'll explore, what this means for our understanding of mathematical structures, kind of in this new way.
Yeah, it's exciting stuff.
Yeah. So the paper kicks off, I guess, by, emphasizing how important multiplicative structures are in homotopy theory. And we're talking about things like, xn, the n-fold tensor products.
Yeah.
Analyzing these is really, essential for understanding how spaces are interacting multiplicatively.
Yeah, absolutely. They're kind of fundamental. And then, this paper's really looking at how they behave in the parametrized setting.
Right. And they also mention norm functors, which are these, really important tools in equivariant higher algebra. And those help us study, spaces with symmetries, which is, a very important aspect of homotopy theory.
Symmetry plays a huge role, and these norm functors kind of give us a nice lens to view it.
Yeah. Now, to really set the stage for their work, I think we need to touch on Goodwillie's functor calculus.
Okay.
So think of it, kind of like calculus in the traditional sense, where we're analyzing polynomials to understand functions. Goodwillie's calculus is kind of doing something similar.
Right. Yeah.
But for functors instead.
Yeah. Yeah. It gives us a way to break down those functors into like simpler pieces, polynomial-like pieces.
Right, exactly. And this paper takes Goodwillie's calculus and sort of gives it this parameterized boost.
Okay.
It's like adding a whole new dimension.
Yeah.
To the analysis.
Yeah.
But before we get there, we gotta touch on parameterized category theory just a bit.
Yeah, a little bit abstract, but we gotta cover it.
Yeah. So we're talking about working with objects and morphisms in categories, but they're indexed by another category.
Yeah.
Which is often denoted T.
Yeah. So instead of looking at one category, we're looking at a whole bunch of them that are kind of all related and changing based on this other category, T.
Yeah.
Okay.
And within this framework, we have, parameterized categories and functors and posets, which are partially ordered sets.
Yeah. Posets give us this nice way to study the relationships between all of our different objects that we're going to be looking at.
Okay. So let's zero in on complementable posets. So these are special posets with two key properties.
Okay.
So first, they're distributive.
Okay.
Which means that finite products and coproducts exist and behave according to the distributive law.
Yep.
Just like in algebra.
Yeah.
And then the other cool thing about them is that for every object in the poset, there's a complement.
Yeah.
It's like having like a negation.
Yeah.
For each object.
Exactly.
So the paper gives examples like cubes with specific transition functors that preserve products and coproducts.
Right.
And these complementable posets are important because they set the stage for the next big concept, which is excisable posets. So an excisable poset is a complementable poset, which they denote by L.
Okay.
And it has this special downward closed supposit, which is denoted L.
Oh.
So you can think of it as like you have this L, it's like a subset of L. And if you have an object Y in L, and there's another object X that's like smaller than Y in the sense that there's a morphism from X to Y, then X is also in L.
Okay, so it's like downward closed.
Yeah, exactly.
Yeah.
And what's so fascinating is that this seemingly simple definition of excisable posets, it's a really powerful generalization of this star, of a cube concept that Goodwillie used in his original calculus.
Yeah. The star was like this key thing he used to like see if a functor behaved well with respect to that cube.
Right, exactly. And this is, sort of extending that.
Yeah, to this much broader setting.
To a much broader setting, yeah. It's remarkable.
Yeah.
So speaking of unlocking things, let's define excision and excisive functors. So the paper introduces this concept of successive functors.
Okay.
And these are functors that send diagrams in one category,
Okay.
which are built using left-can extensions
Okay.
from our supposed L
Okay.
to limit diagrams in another category.
Oh, wow. Okay. So they take these diagrams that are kind of built with L and do something special to them.
Right, exactly. And it's a core concept in Goodwillie's calculus and its generalization here.
Okay.
And it links back to this idea of n-excisive functors.
Okay, so n-excisive functors, that's like saying a functor is polynomial of like degree at most n.
Right,
Right.
exactly.
Yeah.
Now, let's talk about how we can actually approximate, functors with excisive ones using something called excisive approximations,
Okay.
which they denote pay.
Okay, so it's like in regular calculus, we find a polynomial to like best approximate a function.
Right, exactly. And one of the really cool things about this paper is they provide an explicit formula for pay.
Oh, wow. Okay, so we can actually calculate it.
Yes. And this formula is a game changer because it gives us a concrete way to calculate these approximations.
That's super useful. Yeah.
Right. It's it's like a powerful tool that we can use to break down these complex functors into simpler pieces.
Right. Yeah, I see that.
But now, for a seemingly unrelated detour, let's talk about a classical result in equivariant stable homotopy theory.
Okay.
So Wirth-Miller's theorem states that if you invert representation spheres,
Okay.
orbits become self-dual
Right. Yeah.
in a specific category. It's a cornerstone of the field.
It is.
But the connection to spheres has always felt a bit mysterious.
Yeah, a little bit. Yeah. Like we know they're important, but what are they doing there?
Right. And this is where the paper's generalization comes in.
Okay.
They introduce these parameterized cubes and spheres, which are defined in a way that mirrors traditional cubes, but within this parameterized world.
Okay. So we've got like families of cubes, I guess.
Yeah.
Each one's indexed by our category T.
Exactly. And within these cubes, we can define things like singleton inclusions,
Okay.
which mirror the inclusion of subsets in the classical cubes.
Okay.
And using these cubes, they define parameterized suspension and loop functors,
Okay.
which are very important in homotopy theory
Yeah.
for understanding how spaces are connected,
Right.
and how they behave when you shift them up or down in dimension.
Yeah. Yeah. That's a powerful way to think about them.
Yeah. And this leads to their definition of parametrized spheres,
Okay.
which are these objects that behave like spheres,
Right.
but within this parametrized framework.
Okay.
They're a generalization of the familiar spheres.
That's right.
And they play a very surprising role in the paper's results.
Okay.
Now, to connect these parameterized spheres back to that mysterious result, we've got singleton and spherical excision. So the paper defines these two types of excision: singleton excision and spherical excision,
Okay.
which relate to the parameterized cubes and spheres.
Right. Okay.
And they make this really crucial observation,
Okay.
which is that a spherically excisive functor is automatically singleton excisive.
Oh, okay. So if it behaves well with respect to those parameterized spheres, it's also good with those singleton inclusions.
Right.
Okay.
Which, remember, those singleton inclusions were related to semiadditivity.
Okay. Yeah, yeah. So things are starting to come together here.
Right.
Yeah.
So it's like if a functor behaves well with respect to these parameterized spheres, it automatically behaves well with respect to these singleton inclusions.
Yeah.
So that's kind of where we're going with this.
Okay.
So we've set the stage. We've got these parameterized cubes and spheres, these notions of excision.
Yeah.
And we're starting to see how they might connect to semiadditivity.
Yeah. And those mysterious spheres from before.
Exactly. So I think we should move on to part 2 and see how it all comes together.
All right, let's do it. I'm ready.
Okay, great.
Okay, so we've laid all this groundwork with parameterized cubes and spheres and this concept of excision. And now we're going to see how they actually use these tools to kind of shed new light on a classical result, Wirth-Miller's theorem.
Okay, yeah. So Wirth-Miller's theorem, just to remind everybody, that's the one that says if you invert these representation spheres,
Right.
then orbits become self-dual.
Yeah.
Right.
Yeah.
In this specific category.
Yeah.
And it's a really foundational result. But the traditional proof relies on these geometric arguments
Yeah.
that don't easily generalize to this parameterized setting.
Exactly. And that's where Hilman and Linskens are taking this really interesting, purely algebraic perspective.
Okay. Yeah.
And they're really cleverly using the sort of special properties of these atomic orbital categories.
Right.
The types of categories that we're focusing on here.
Right. These categories that have these structures that are related to orbits and pullbacks and
Yeah,
and all that.
exactly.
Yeah. So it's really fascinating how they connect their parameterized framework to this classic result.
Yeah, so they really key in on this fact that within these atomic orbital categories, our parameterized cubes, those families of cubes indexed by t, they actually encode a parameterized semiadditivity.
Okay, so remind me again, what exactly does semiadditivity tell us?
Right. So essentially, it's describing how a functor behaves, with respect to sums of objects.
Okay.
It's kind of a way of saying that the functor respects the additive structure of the category.
Okay. So these parameterized cubes are capturing this additive behavior. How does that work?
Right. So remember those singleton inclusions that we talked about, within the cubes?
Mm-hmm.
Those play a really crucial role. So the authors define this type of excision, which they call singleton excision.
Okay.
Which essentially means that a functor, behaves nicely with respect to these singleton inclusions.
Right.
So they're creating this beautiful bridge between, functor calculus and this idea of the additive structure of categories.
Yeah. So they're using excision, which is this concept from functor calculus to understand semiadditivity, which is this property that's related to the additive structure of categories.
Exactly. Yeah, they're really bringing those two ideas together.
Okay. Okay. Cool.
And then recall that we also defined spherical excision.
Right.
Involving those parameterized spheres, which are those objects that kind of generalize the idea of spheres.
Right. Those families of spheres, I guess, in different dimensions.
Yeah. Exactly.
Yeah.
And so here's the really crucial observation. A spherically excisive functor is automatically singleton excisive.
Oh, okay.
So it sounds simple, but it really has some profound implications.
So it's like, if a functor behaves well with respect to these parameterized spheres, then it automatically behaves well with respect to the singleton inclusions.
Exactly, yeah.
Which we know are kind of related to semiadditivity.
Yeah.
Okay, so it's like a domino effect here.
Yeah, exactly. And this is where Hilman and Linskens make their move. They use their powerful theorem about excisive approximations.
Right.
The one that we talked about before.
Which gives us that formula.
Exactly, yeah.
Yeah.
So by applying their theorem to the identity functor,
okay,
they show that if a category is what they call spherically faithful,
okay,
which means that the suspension functor associated with these parameterized spheres, right,
is well behaved, then the identity functor is spherically excisive.
Okay.
And since spherical excision implies singleton excision, we know that the identity functor is also singleton excisive.
Right.
And because singleton excision is tied to semiadditivity,
right,
we can conclude that the category itself is parameterized semiadditive.
Wow. Okay. So it's like they've woven this really intricate web of logic here.
Yeah.
Connecting these seemingly disparate concepts.
Yeah, it's a really remarkable, chain of reasoning.
Yeah.
And it reveals this deep connection between the invertibility of these parameterized spheres
yes.
and the semiadditivity of the category.
Okay. So how does this all kind of circle back to Wirth-Miller's theorem?
Right. So what Hilman and Linskens are essentially doing is they're giving us a new proof.
Okay.
Of a kind of generalized version of Wirth-Miller's theorem.
But without relying on those geometric arguments of the traditional proof.
Okay.
So they show that in a suitable parameterized setting,
right,
if a category is what they call spherically invertible,
okay,
which means that the suspension functors associated with these parameterized spheres are equivalences,
okay,
then the category is parameterized stable.
Right. And parameterized stability implies implies semiadditivity.
Exactly. Yeah.
Which was kind of the key consequence of Wirth-Miller's theorem.
Exactly. Yeah, they've really kind of illuminated the sort of underlying structure of this classical result.
It's incredible how they've taken this really complex puzzle, of parameterized category theory, homotopy theory, these classical results, and shown how it all fits together. It's elegant and surprising.
It really highlights, the interconnected nature
of mathematics and the power of generalization,
Absolutely.
Yeah. But we're not done yet. There's still more to explore in Hilman and Linskens' work.
Okay. Well, let's move on to the final part and see what other insights they have in store for us.
Sounds good.
All right, so we're back for the final part of our deep dive into parameterized functor calculus, and my brain is still buzzing a little bit from everything we've talked about so far about spheres and excision and semiadditivity, but I'm really excited to see what other gems Hilman and Linskens have uncovered in their research. What's really striking me is how their work is not just reinterpreting existing results, but it's also like paving the way for all this exciting new research.
Yeah, it really feels like they've given us this new toolbox to work with. Like it could revolutionize the way we think about parameterized mathematics.
Right, as a whole.
Yeah, so can you give me any specific examples of areas where this framework could be applied?
Oh yeah, tons. Take algebraic K-theory, for instance, which is the study of rings and their invariants. And it's a really challenging field.
Yeah.
But parameterized functor calculus could provide new tools for understanding the K-theory of rings with group actions or other parameterized structures.
So we could potentially tackle problems in K-theory.
Yeah.
That we couldn't before.
Exactly. Yeah. That's just one example, though. It could also have really significant applications in the study of equivariant stable homotopy theory, which is dealing with spaces with symmetries. And we could see a much deeper understanding of this intricate relationship between representation spheres and orbits. Right.
Yeah. Which makes sense, considering they already kind of gave us this new proof of a generalized Wirth-Miller's theorem.
Exactly. Yeah. But what's really remarkable is how their work just highlights the power of abstraction in mathematics. By taking these existing concepts and generalizing them to this more abstract setting. They've really unveiled all these unexpected connections and shed new light on areas that seem totally unrelated.
It's like they've given us this new pair of glasses to see the mathematical world with.
Exactly.
And we can see these patterns and relationships that we couldn't see before.
Yeah, we're getting the bigger picture now.
Yeah, exactly. And this bigger picture leads to all these new questions.
Oh yeah.
And exciting new avenues of research.
Yeah.
It's really exciting to think about all the potential discoveries that could come from this line of research.
Yeah.
But before we get too carried away with the future, I want to kind of go back to something that really intrigued me in the paper. So they mentioned that the traditional geometric approach to Wirth-Miller's theorem doesn't really generalize to the parameterized setting.
Wow.
Why is that?
Yeah, that's a really good point. So the classical proof really relies on these techniques from equivariant smooth manifold theory, which don't have like straightforward analogs in the parameterized world.
Okay, so their approach, this purely algebraic categorical approach, it kind of allows us to get around those geometric limitations.
Exactly. Yeah, it's giving us a way to circumvent those issues. Okay,
so this raises a really, really interesting question then.
Yeah.
What new insights do we get from this shift in perspective? What are the implications of having this proof that doesn't rely on this geometric intuition?
Yeah, it really makes you think differently about the nature of these objects and how they're all related.
That's a really profound question, and one that I'll definitely be thinking about as we wrap up this deep dive. Hilman and Linskens' work has really opened our eyes to
Yeah.
this vast new landscape
Absolutely.
of parameterized mathematics.
Yeah.
And their insights are really a testament to the power of abstraction and generalization and just the interconnected beauty of mathematical ideas.
Couldn't have said it better myself.
Yeah.
Yeah, it's a fantastic paper. It's really innovative and a sign of really exciting things to come in this field.
Well, it's safe to say our brains have gotten quite the workout today. So thank you for guiding us through this intricate and fascinating world.
It's been my pleasure. And to our listeners, we encourage you to really dig into this work yourselves.
Yeah.
Share your aha moments. And let's keep this conversation going. The journey of mathematical discovery is always more rewarding.
Yeah.
When it's shared.
Absolutely. So until next time, keep exploring, keep questioning, and keep diving deep into the world of knowledge. All right, let's take a deep dive into this paper on parametrized functor calculus.
Sounds good.
It's called Parametrized Functor Calculus, Excision, Spheres, and Semiadditivity.
Okay.
And it's by Kaif, Hilman, and Linskens.
Right.
And it just came out very recently on October 30th, 2024.
Yeah.
I know that you're already pretty familiar with the basics, so I think we can jump
let's jump into it.
right into some of the exciting details.
Yeah. Definitely.
So basically, they're building this new framework for studying mathematical objects that have these really intricate multiplicative structures.
Yeah, that's a good way to put it. It's really interesting how they generalize Goodwillie's functor calculus to this parametrized setting.
Yeah.
It's like they're taking this really powerful tool for analyzing functors that behave like polynomials, and they're adapting it to handle even more complex situations.
Yeah, you mentioned these multiplicative structures being really key here. Absolutely.
Yeah.
Can you maybe expand on that a little bit?
Sure.
Like, where do these structures actually pop up?
Yeah.
And why do they make things so tricky?
Think about just basic multiplication of numbers.
Right.
Or maybe tensor products in algebra, or even smash products in topology.
Okay.
These are all examples of multiplicative structures, and they create these really intricate relationships between objects, which traditional functor calculus doesn't always handle very well.
So this new parametrized version gives us a better lens for understanding these interactions.
A much better lens.
Okay, cool.
Yeah. It's like we're upgrading our mathematical toolkit.
Yeah.
Yeah.
So they're not just working in a vacuum here.
Right.
This research builds on some previous work.
Oh, yeah, absolutely. It builds on some really important work.
On equivariant calculus?
Yeah, on equivariant calculus by people like Blumberg, Dotto, and Moy.
Right. And they're sort of taking those ideas
Yeah, they're taking these existing ideas
and extending them.
To an even broader framework.
Okay, so we've got this new souped-up version of functor calculus.
Yes.
Where do these excisable posets come into play?
They are absolutely crucial.
They seem to be pretty central to the whole thing.
You can think of them as a generalization of the cubes that are used in traditional functor calculus.
Okay.
Remember how cubes let you break down complex objects into simpler pieces?
Like a three-dimensional grid where you can analyze each cell individually.
Exactly. Excisable posets do something very similar.
Got it.
But in a more abstract setting.
Okay.
The paper defines them in a way that captures the essence of these cubes and allows for a similar kind of decomposition.
Okay.
And the key property here is what's called complementability.
Complementability?
Yeah.
What does that mean in this context?
It basically means that these posets can be broken down into orthogonal pieces. It's like separating out the different dimensions of a cube.
Right.
So you can analyze each direction independently.
So it's all about having this structured way to decompose these posets and study their parts.
Precisely.
Okay, and you mentioned faces of excisable posets.
Yes, the faces of excisable posets.
I'm guessing that's kind of analogous to the faces of a cube.
You got it.
Okay.
And just like with a cube, these faces help us understand the relationships between different levels of excisiveness of functors.
Right, like how a one excisive functor is like a linear approximation.
Yes.
And a two excisive on is like a quadratic approximation.
Precisely. And the paper goes into detail about how these faces of excisable posets allow for a very precise analysis of these different levels of excisiveness.
Okay, so we can break down these posets
Yes.
into these manageable pieces.
Right.
But how do we actually use them to analyze functors?
That's where excisive approximations come in. It's like approximating a complicated function with a simpler one, like a polynomial.
So if I have a really gnarly functor,
Exactly.
I can find a simpler one that's
Yeah, you can find a simpler one that's close enough in some sense.
close enough.
Yes.
Okay.
And what's really cool is that the paper gives us an explicit formula.
Oh, a formula.
Yes, an explicit formula
That's great.
for calculating these approximations in this parametrized setting.
So we're not just saying that approximations exist.
Right.
We're saying we know exactly how to do it.
We know exactly how to do it.
That's impressive.
Yeah, and it's not just any formula.
Yeah.
It's very specifically tailored to this framework of parametrized functor calculus.
Okay, so where does all of this lead? What kind of problems can we tackle with this new machinery?
The paper takes kind of a fascinating turn
Okay.
and applies this framework to something seemingly unrelated at first,
Okay.
which is parametrized semiadditivity.
Parametrized semiadditivity.
Yeah, it's a concept from equivariant homotopy theory.
Okay.
And it involves the invertibility of certain special objects called representation spheres.
Representation spheres.
Yes.
I feel like we're jumping into a whole different area of math here.
It might seem like a leap,
Yeah.
but there's a deep connection.
Okay.
These representation spheres capture the symmetries of group actions.
Okay.
And there's this famous theorem by Wirth-Muller
Okay.
that describes how they become self-dual in a particular mathematical context.
Self-dual. So they're like their own mirror images in a way.
You could say that.
I've done
It's a
it.
special property that has very deep implications.
Okay.
And Nardin, building on Wirth-Muller's work,
Right.
extended these ideas to a more general context.
Okay.
And that's where this parametrized semiadditivity comes in.
So this paper is bridging parametrized Functor calculus
Exactly.
with this world of equivariant homotopy theory
Yeah.
and these mysterious spheres.
It is. And the bridge is built using these clever parametrized cubes.
Parametrized cubes.
Yes.
Excisable posets.
Right. It's all starting to feel like a very elaborate puzzle.
It is, but the pieces fit together beautifully.
Okay.
These parametrized cubes allow us to apply calculus-based methods to study this problem of parametrized semi-additivity.
Okay.
And get this,
Yeah.
they use these cubes to construct
Yeah.
parametrized spheres.
Wait, more spheres.
More spheres.
Are these like the representation spheres that you mentioned earlier?
They are a generalization of those.
Okay.
But the key is that they're built using these parametrized cubes,
Right.
which allows us to analyze them using the tools of functor calculus.
So they're taking this new calculus
Exactly.
and applying it to objects that were previously studied using very different techniques.
It's like we've discovered a secret passage
Yeah.
between these two seemingly separate areas of mathematics.
Okay, I'm hooked.
Great.
What kind of insights does this connection reveal? Well, one of the big results is a brand new characterization of parametrized stability.
Okay.
Remember, parametrized stability, as defined by Norden, involves two conditions,
Okay.
fiber-wise stability and this parametrized semi-additivity that
That's
we've
right.
been talking about.
Two conditions.
Yeah. But this
So
research...
this sounds complicated.
It is a little bit, but this research sheds light on this deep connection.
Okay.
They show that the invertibility of these specific parametrized spheres
Right.
is directly linked to this concept of parametrized semi-additivity.
So instead of checking two separate conditions,
Yeah,
we can maybe just focus on the invertibility of these spheres.
exactly.
That sounds promising.
It is very promising.
Okay, so they're not only generalizing these classical results,
Yeah.
but also
They're providing new perspectives
providing new perspectives.
and potentially opening up new research avenues.
That's amazing.
It is amazing stuff.
And what's particularly striking
Yeah.
is that these ideas about self-duality and stability
Yeah.
aren't limited to just equivariant homotopy theory.
Right. They have broader implications for mathematics as a whole.
So it's not just about proving these theorems.
It's not just about proving theorems.
It's about revealing deeper connections
Exact.
and potentially changing how we think about these fundamental concepts.
Precisely.
Wow.
And it all starts with this beautifully simple idea of excisable posets.
I'm starting to see the power of these posets.
Yeah.
They might seem really abstract at first,
They do seem abstract.
but they're unlocking this whole new world
Yeah.
of mathematical insight.
A whole new world of mathematical insight.
Okay. So speaking of those spheres,
Yeah,
you mentioned that they're key
they are key.
to understanding parametrized stability.
Yes,
Can you tell me a little bit more about that?
absolutely.
I'm ready for some nitty-gritty details.
Let's delve into how they characterize parametrized stability using these spheres.
Okay.
It's really quite elegant. So you're really interested in how these parametrized spheres actually connect to parametrized stability. Yeah.
It all boils down to a couple of key theorems in the paper.
Okay.
They don't actually give them labels, but just for our discussion, let's call them Theorem B and Theorem C.
Okay. Theorem B and Theorem C.
Right.
Let's start with Theorem B.
Okay.
What's the gist of that one?
Theorem B essentially gives us a way to detect this T semiadditivity property
Okay.
just by checking if those specific spheres are invertible.
Okay.
It says that if you have a pointed parametrized category
Okay.
that satisfies certain technical conditions,
Yeah.
being what's called parametrized by complete,
Right.
and something called spherically invertible,
Okay.
then that category is automatically T semiadditive.
Okay. I'm following so far.
Okay, good.
But let's unpack some of those terms.
Sure.
What exactly does it mean for a category to be pointed?
A pointed category simply means that it has a special object,
Okay.
often called a zero object,
Right.
that acts like a kind of neutral element for certain operations.
Right.
You can think of it like the number 0 in arithmetic. Okay. Adding 0 to anything doesn't change its value.
Right. So a pointed category has a kind of grounding point for
Yes.
its objects.
Yes, exactly.
What about parametrized by complete?
Okay.
That sounds a little technical.
It is a bit technical.
Yeah.
But basically it means that the category is well behaved with respect to limits and colimits.
Okay.
These are very fundamental constructions in category theory,
Right.
ways of building new objects from old ones.
Okay.
You need these tools to do any serious work in this area.
Got it.
Yeah.
So we need a category that has a zero object.
Right.
And that plays nicely with limits and colimits.
Exactly.
Now, what about this spherically invertible condition?
Okay.
That sounds like it's at the heart of this theorem.
You're absolutely right.
Yeah.
This is where those parametrized spheres we talked about earlier come in.
Okay.
A category is spherically invertible if suspending an object
Right.
along any of those parametrized spheres
Right.
results in an object that has an inverse in a specific sense.
It's like saying that those spheres act like invertible elements within the category.
Interesting.
Yeah.
So Theorem B is linking this invertibility of the spheres to the category's
That's what we
overall
started.
structure.
Yeah.
But we've been dancing around this T semiadditivity thing.
Right.
Can you remind me why we should even care about that?
Yes.
Like, what makes it so special?
T semiadditivity is a very powerful property
Okay.
that captures a lot of information about how a category behaves.
Okay.
In a way, it generalizes the familiar idea of additivity from arithmetic.
Okay.
Remember how we talked about those representation spheres becoming self-dual?
Yeah.
Well, T semiadditivity provides a much broader framework for understanding that self-duality
Okay.
in a much wider range of mathematical contexts.
So in a T semi-additive category,
Right.
things behave in a more predictable, structured way.
Exactly.
Kind of like how
Yeah.
the rules of arithmetic govern the behavior of numbers.
Exactly.
Yeah.
And what makes Theorem B so remarkable is that it gives us a way to detect this very complex property,
Right,
this
yeah.
T semiadditivity,
Right.
just by checking the invertibility of those specific spheres.
It's a very elegant connection.
This is a very elegant connection.
But I have to ask, you
Yeah.
keep mentioning this T.
Right.
What does the T stand for?
Good catch.
Yeah.
The T refers to the base category over which we're parametrizing.
Okay.
Remember how this whole theory is about extending
That's-
traditional functor calculus to a parametrized setting?
Yeah.
Well, that base category is the parameter space,
Okay.
the context in which everything is happening.
So T kind of sets the stage.
Yes. T sets the stage.
And then we look at categories that are built over this base category T.
Exactly.
Okay. And for Theorem B to work,
Yes.
this T needs to be what they call a locally short atomic orbital category.
Right.
I have to admit, some of those words are a little intimidating.
I understand.
Yeah.
Let's break them down a bit. Atomic means that the category has a kind of simplicity to its structure.
Okay.
Its morphisms can't be broken down any further.
Okay.
Orbital refers to a specific property related to pullbacks, which are another important construction in category theory.
Okay.
And locally short means that the category doesn't have infinitely long chains of morphisms
Okay.
within its slices.
Slices. Now I'm getting lost in the jargon.
My apologies.
Yeah.
A slice of the category is essentially a subcategory
Okay.
that focuses on a particular object.
Right.
And locally short just means that these slices have a finite depth, so to speak.
Okay.
It's a technical condition to ensure that the category is well behaved for this theory.
So we need this special kind of base category,
Right.
atomic,
Orbital,
and locally short
and locally short.
for theorem B to apply.
Yes.
And if we have that and our category over it is pointed and bicomplete,
Right.
and those special spheres are invertible,
Yes.
then we know it's T semiadditive.
It's a powerful result with broad implications.
Yeah.
The paper even gives some very concrete examples
Okay.
of these locally short atomic orbital categories, like
Right.
the orbit category of a finite group,
Right.
or categories of vector spaces with certain restrictions.
So this theory has real mathematical
It
applications.
does.
Real world applications.
That's always exciting to see.
It is.
But you know what's been bugging me?
Yeah.
You said that this theorem helps characterize parametrized stability.
Right.
But so far, we've only talked about one of the conditions,
Yeah.
this T semiadditivity.
Yeah.
What about the other condition,
Right.
the fiber-wise stability?
Okay.
How does that fit into all of this?
That's a great question.
Yeah.
And it leads us very nicely to the second key result, theorem C.
Okay.
This theorem brings fiber-wise stability into the picture
Okay.
and really ties the whole story together.
All right. So let's recap a little bit.
Okay.
We've got theorem B.
Which gives us this really elegant connection
Yeah.
between the invertibility of those special spheres
Right.
and the T semiadditivity property.
Exactly.
But you mentioned theorem C
Yeah.
brings in this whole other condition,
Yeah.
fiber-wise stability.
Right.
I'm really curious to see how that fits into the puzzle.
Okay, well, theorem C is where it all comes together. It
Okay.
basically says that if you have a pointed parameterized category
Okay.
that's not only bicomplete,
Okay.
but also something called presentable,
Presentable.
and we'll come back to what that means in a second,
Okay.
then being parameterized stable
Okay.
is the same as being spherically invertible.
Whoa, hold on.
Yeah.
So you're saying that under the right conditions,
Yes,
parametrized stability is equivalent
that's right.
to spherical invertibility.
It is.
That's a pretty bold statement.
It is a bold statement, and it's a beautiful result.
Wow.
It really highlights how those special spheres
Yeah.
hold the key to understanding parametrized stability in a lot of situations.
Okay.
But remember, parametrized stability is about extending this concept of stability
Right?
from ordinary homotopy theory
Right.
into this broader parametrized setting.
Okay.
And it's not just about the suspension functor being an equivalence.
Right.
It also needs this T semiadditivity piece to work correctly.
So there are these two intertwined aspects
Exactly. Two intertwined at.
to parametrized stability.
Yes.
And this theorem is saying that under certain conditions,
Right.
we can capture both of them
We can capture both of them.
just by looking at whether those spheres are invertible.
Exactly.
This is getting really interesting.
It is.
Okay, so we know from theorem B
Yes.
that spherical invertibility implies
Right.
T semiadditivity.
Exactly.
But how does theorem C show that it also implies this
Okay.
fiber-wise stability piece?
That's a great question.
That's the part I'm missing.
That's the part that's a little bit subtle.
Yeah.
Here's where it gets really clever. The paper leverages a known result about parametrized stable categories,
Okay.
namely that they're always modules
Okay.
over a very specific and well-understood category,
Okay.
which is denoted by SP,
All right.
which is the category of spectra.
Okay, spectra. Those are pretty fundamental objects
They are.
in homotopy theory.
They are very fundamental objects in homotopy theory.
Okay.
And spectra have a lot of nice properties.
Yeah.
One of them
Okay.
is that the spheres within the category of spectra are always invertible.
Interesting.
Yes.
But how does that connect back to our category?
Okay.
The one we're trying to show is parameterized stable.
Right. So because our category,
Let's call it C.
let's call it C
For now.
for now,
Okay.
is a module over SP.
Right?
There's a way to kind of multiply
Oh.
objects in C by objects in SP. And because the spheres in SP are invertible,
Yeah.
it forces the corresponding spheres in C to
Wow.
also be invertible.
That's-
It's like the invertibility in SP
Yeah.
is infecting C.
So that takes care of the spherical invertibility part.
Yes.
But why does that automatically mean
Okay.
that C is also fiber-wise stable?
Right. Well, remember that in a parameterized stable category,
Yeah.
each fiber,
Yeah.
which is just the restriction of the category over a particular object in the base category,
Right.
should be an ordinary stable category.
Okay.
And in an ordinary stable category,
Yeah.
The suspension functor being an equivalence
Yeah.
is enough to guarantee stability.
Right. So we just need to show that the suspension functor
Exactly.
is an equivalence on each fiber of C.
That's all we need to show.
Okay.
And that's where spherical invertibility comes in.
Okay.
Since C is spherically invertible,
Yeah.
suspending any object
Right.
along those special parameterized spheres
Right.
gives you an equivalence.
Okay.
But when you restrict to a fiber,
Yeah.
those parameterized spheres essentially collapse into ordinary spheres.
So the spherical invertibility, when restricted to a fiber,
Yes.
just becomes the ordinary invertibility of spheres.
Exactly.
Which then implies the suspension functor is an equivalence on that fiber.
Got it.
Boom. Fiber-wise stability.
Boom. Fiber-wise stability.
That's so cool.
It's a really beautiful chain of reasoning.
Yeah.
It demonstrates these deep connections between all of these different concepts: spherical invertibility,
Right.
T semiadditivity, fiber-wise stability, and ultimately parametrized stability.
This paper has blown my mind.
It's a great paper.
It's given us this whole new set of tools
It has.
for understanding these incredibly complex categories.
Yes, incredibly complex categories.
And what's even more impressive is how they managed to do all of this
I know.
with such an elegant and streamlined approach.
It's really remarkable.
It's inspiring work.
It is.
They're not just pushing the boundaries of mathematics.
Right.
They're doing it in a way that's beautiful.
Yeah.
And even, dare I say, fun.
I would agree with that.
This has been an amazing deep dive.
It has been a pleasure.
Thank you so much for walking me through this paper.
It was my pleasure. It's always great to talk about such interesting mathematics.
And listeners, if you're up for a challenge
Yes.
and you want to explore the cutting edge of category theory
Absolutely.
and homology theory, definitely check out this paper.
Yeah, great paper.
Until next time, keep exploring the amazing world of mathematics. Welcome back, everybody. Today, we're going to be diving into parametrized functor calculus.
Ooh, exciting.
We have a paper here, hot off the press, just published today, October 30th, 2024,
Wow.
titled Parametrized Functor Calculus, Excision, Spheres, and Semiadditivity.
This is a paper that's been generating a lot of buzz in the community. A lot of people are excited to see where this goes.
Yeah, I'm just looking at the title here. Parametrized Functor Calculus. It sounds like an extension of Goodwillie calculus.
That's exactly right. Goodwillie calculus gave us really powerful tools to study functors that, kind of roughly speaking, behave like polynomials.
Okay.
Like if you have the functor that takes a space x and it sends it to its nth tensor power, like x tensor n.
Right.
This new paper, though, it seeks to generalize those ideas to a much broader class of functors.
So we're talking about functors that depend on some parameter.
Yeah, exactly.
Huh.
Think of it like this. Imagine you have like a family of spaces that vary, continuously based on some parameter. Parametrized functor calculus lets us analyze how functors behave across that whole family. It gives us a deeper understanding of the underlying mathematical structures.
Got it. And what about this excision, spheres, and semiadditivity part of the title?
Well, those are some of the key concepts that the paper really explores. Excision refers to a certain property of functors. It basically allows us to break down complicated objects into simpler pieces. Spheres, those are very special objects. They play a really fundamental role in homology theory. And semiadditivity, that's a condition that captures certain algebraic structures.
Okay. I think I've started to get a sense of the terrain we're going to be exploring. Let's dive into the paper itself. Page 1 starts by setting the stage, highlighting that connection to Goodwillie calculus and mentioning the importance of multiplicative structures in homology theory. What stood out to you?
Well, the paper kind of jumps right into the deep end
Okay.
by reminding us of Goodwillie's fundamental insight, which is that a lot of the functors we care about can be approximated by simpler ones.
Okay.
That satisfy an n-excisive condition. This is kind of like saying we can break down a complex function into a series of simpler functions,
I see.
much like a Taylor series expansion in calculus.
Right.
But this paper, what they're trying to do is push those ideas further, right? They're taking those ideas into this realm of parametrized categories and functors.
Exactly.
They want to understand how this excisive approximation machinery works when we have functors that depend on these parameters. And they're particularly interested in understanding these multiplicative structures like norm functors, which are just all over the place in homotopy theory.
Okay, so that's the big picture. Now, on page 2, they get into the nitty-gritty. They define parametrized categories and parametrized functors. These seem to be like the fundamental building blocks of their theory.
Oh, absolutely. You can't do anything without those.
Right.
So a parametrized category is essentially a family of categories that vary continuously over some base category. We often call that T. You can kind of think of it as a category where the objects and the morphisms themselves, they come equipped with this extra data that lives in T.
So it's like adding another layer of structure, a T dimension to our category.
That's a great way to put it, yeah. And then a parametrized functor is, it's just a map between these T categories that respects this extra, this T structure.
Right.
They kind of live in this world called funtop cat. That's the category of all functors, from T to the category of all categories.
So functors of functors.
That's right, yeah.
Now, the paper also brings in these things called posets, which are partially ordered sets. What role do they play in this story?
Oh, posets are absolutely crucial. They provide a way to organize information. You can track dependencies between different objects. Think of a poset as like a set with a specific order relation, like a family tree, where the order is determined by ancestry. In this paper, they're looking at special types of posets called complementable posets.
Complementable posets?
Yeah.
What are those?
In a complementable poset, every element has what we call a complement. It means that for every element x in the poset, there's another element, we call it x complement, such that when you combine them using what we call the least upper bound, you get the biggest element in the poset. And when you combine them using the greatest lower bound, you get the smallest element.
Okay.
So the least upper bound, you can kind of think of that like finding the smallest element that's bigger than both x and x complement.
Got it.
And the greatest lower bound is the opposite, the smallest element that's smaller than both.
Why are these complementable posets so important in this context?
Well, because they let us break things down. They let us break down objects into smaller, more manageable pieces. And the paper gives the example of a cube with what they call coproduct preserving transition functors between its faces.
Coproduct preserving transition functors. Could you unpack that a little bit?
Sure. A coproduct is like a way of combining objects in a category. You're like taking the disjoint union of sets, but in a more general setting. In this example, the transition functors between the faces of the cube, they're required to preserve these coproducts.
Yep.
So if you take two faces of the cube and you combine them using the coproduct, the result is still a face of the cube. That structure turns out to be a really great example of a complementable poset.
Okay, I see. So we've got these complementable posets. They're helping us break things down. And then they introduce this idea of excisable posets.
Right. So an excisable poset is a complementable poset with an additional condition. You have a complementable poset L, and then you have a specific subset of L, which is called L check. And that subset is what we call downward closed.
Downward closed. What does that mean in this context?
It means if an element y is in L check, and there's another element x that's smaller than y in terms of the poset, then x has to also be in L check.
Okay.
So it's like a subset that's closed under, going down the order relation.
I see. So excisable posets are these special complementable posets with this downward closed subset. What makes them so important for this parametrized functor calculus idea?
Well, because they provide exactly the right setting for defining and studying these excisive functors, which are really the heart of this whole theory.
Okay.
These functors, they behave in a very specific way with respect to certain diagrams in our parametrized categories.
All right, so that's where it starts to get really interesting.
It does. But before we jump into all of that, the excisive functors and everything, let's take a closer look at the example they give of an excisable poset.
Okay.
The inclusion of subsets of size at most 1 in an n+1 dimensional cube.
Okay.
This might seem like kind of a simple example, but it turns out to be deeply connected to Goodwillie's original definition of these excisive functors.
Okay, let's dive into that example a little bit. How does a cube relate to this idea of excisable posets?
Well, think of an n+1 dimensional cube as a poset. The elements of the poset are the vertices of the cube, and the order relation is given by inclusion. So a vertex V is less than or equal to a vertex W if V is a corner of the face that W represents.
Okay.
Now, if you consider the subset of vertices that correspond to subsets of size at most 1, this includes all the individual vertices and The empty set, which you can kind of think of as like the bottom element of the poset,
Right.
that subset is downward closed, right? Because if a vertex is in the subset, then any vertex that's a corner of its corresponding face is also in the subset.
So we have this cube, we can view it as a poset, and we have this special subset of vertices that's downward closed. How does this connect to the concept of an excisive functor?
Well, an excisive functor in Goodwillie's original formulation is a functor that satisfies a certain excision property with respect to cubical diagrams. This excision property basically says that the functor behaves nicely when you glue together certain pieces of the cube.
Right.
And this property is very closely tied to the structure of this excisable poset that we just described.
Okay, so this simple example of the cube, it's actually a key insight that links the classical theory of Goodwillie calculus to this new, more general framework of excisable posets.
Yeah, you got it. And as we go deeper into the paper, we're going to see how this new framework allows us to extend and refine Goodwillie's original ideas in really powerful ways.
This is getting really exciting. I can't wait to see where this leads.
Me too. The paper's just getting started. There's a lot more to uncover.
Okay, let's turn to page 3. Now we're getting into the heart of the paper's contributions.
Yeah, this is where things start to get really interesting.
They introduce this concept of a successive functor, which seems to be a generalization of Goodwillie's n-excisive functors.
That's right. A successive functor is a functor that satisfies a certain excision property with respect to an excisable poset, which we call sus. Remember, an excisable poset that consists of a complementable poset L and this downward closed subset L check. The definition of sus excision involves looking at these diagrams in the parametrized category that are indexed by this poset L and requiring that the functor sends those diagrams to either Cartesian or co-Cartesian diagrams, depending on whether an element is in L check or not.
Okay, I'm trying to keep up. So we've got these special diagrams. They're indexed by the poset, and a sus excisive functor sends them to either Cartesian or co-Cartesian diagrams, depending on where the elements in the poset land. Can you remind me what those diagrams are again?
Sure. So let's start with Cartesian diagrams. Imagine you have a diagram where every square in that diagram is a pullback square.
Okay.
A pullback square is a way of taking what we call the fiber product of two objects over a third object. It's like a really fundamental construction in category theory that captures the idea of gluing objects together in a specific way. So Cartesian diagrams are diagrams where all those squares are glued together using pullbacks.
Like fitting pieces of a puzzle together, where each piece locks into the others perfectly.
Exactly. That's a great analogy. Co-Cartesian diagrams are, they're kind of the dual notion. They're diagrams where every square is a push-out square. And a push-out square is, roughly speaking, the opposite of a pullback square.
Right.
It's a way of gluing objects together along a shared piece. So co-Cartesian diagrams, those are diagrams where all the squares are glued together using push-outs.
Okay, thanks for the refresher.
Yeah.
So these successive functors, they're functors that preserve certain properties of these Cartesian and co-Cartesian diagrams. Why are these diagrams so important in the first place?
Well, they capture these really fundamental ways that objects in a category can be related to each other.
Okay.
You see, Cartesian diagrams, they represent limits, which are ways of taking like the intersection of objects in a category.
Okay.
And co-Cartesian diagrams, they represent colimits, which are ways of taking kind of the union of objects. And these concepts of limits and colimits, they're everywhere in math, right?
Right.
And they play a super central role in category theory.
So these excisive functors are, in a sense, well-behaved functors that respect these fundamental constructions of limits and colimits.
Exactly. And what's really cool is that Goodwillie calculus actually gives us this concrete formula for constructing the best possible approximation of any functor by using these n-excisive functors.
Well, yeah.
It's like you're taking a complex function and breaking it down into a series of simpler functions, just like a Taylor series expansion in calculus.
Okay, so we can approximate any functor using these special well-behaved excisive functors.
Yeah, exactly. And this paper is taking that idea and it's extending it to this world of parameterized functor calculus.
Right.
Theorem A, which they present on page 3, gives an explicit formula for constructing the best possible excisive approximation of any parameterized functor.
Theorem A sounds like a big result. Can you walk us through it a little bit? What's the intuition behind this formula?
Okay, so the formula itself, it's a little technical,
Sure.
but the intuition is actually quite elegant. So the idea is to take your parameterized functor, let's call it f fit,
Okay.
and you want to construct this new functor, we'll call it bef. That is excisive. And it's the closest such functor to f. And this notion of closest, it's made precise by using something called natural transformations,
Right.
which are ways of comparing functors. The formula for PF, it involves taking a certain colimit over a diagram. That diagram is indexed by this poset L. That's part of our excisable poset. So this colimit construction, what it does is it essentially averages the values of f over different parts of the diagram.
Right.
And it results in a functor that satisfies that excision property that we want.
Okay, so we're taking this colimit over this diagram, and it's kind of like taking a weighted average of the functor's values.
Yeah.
And this averaging process, it like smooths out the functor, so to speak, makes it satisfy this excision property.
Yeah, that's a good way to think about it. And what's really nice is that Theorem A gives us this explicit recipe for doing this averaging.
Right.
It's like we have this blueprint for constructing these excisive approximations.
Wow, that's pretty powerful. But before we move on, I have a question. The paper mentions this term differentiability in the context of category theory. What does that even mean?
Oh, that's a great question.
Yeah.
So in this context, differentiability refers to a technical condition on the target category of our parameterized functor.
Okay.
It basically makes sure that certain limits and colimits play nicely with each other.
Got it.
This condition is needed to guarantee that this whole approximation machinery works smoothly. It's kind of like requiring a function to be continuous and differentiable in calculus,
Right.
so that you can take its derivative.
Okay. So it's a technical condition, and it ensures that smooth operation of this approximation process. Okay, I think I'm starting to see the bigger picture here. Theorem A gives us this powerful tool for constructing excisive approximations of these parameterized functors. And this concept of differentiability is like this technical requirement to make sure everything works as expected.
Exactly. Now, with Theorem A under our belt, the paper takes us on this really fascinating journey to explore the world of atomic orbital categories, parametrized cubes, and the connections to these really classical theorems in equivariant homotopy theory.
That sounds really intriguing. Let's turn the page and see what they have in store for us.
All right, on page 4, we encounter these things called atomic orbital categories.
Okay.
The paper dives into their properties and introduces some key examples that are going to play a super crucial role in the discussion that follows.
Atomic orbital categories. The name itself sounds kind of mysterious. Can you give us a sense of what they are?
So imagine a category where every morphism is either an isomorphism or it's not.
Okay.
There are no in-between morphisms. That's the atomic part. The orbital part means that we have these finite coproducts, which are like taking disjoint unions, and pullbacks, which are like taking intersections, but in this specific categorical way.
Okay.
And these categories, they have a very particular structure that makes them really well suited for studying certain phenomena in homotopy theory.
Okay, I think I'm getting a rough picture. So in these categories, morphisms are either all or nothing. And we have these tools of coproducts and pullbacks. Can you give me some examples, some concrete examples of these atomic orbital categories?
Sure. The paper gives us 3 really illuminating examples. So the first one is the orbit category of a finite group.
Okay.
So this category has objects that are sets with an action of that group, and the morphisms are what we call equivariant maps, meaning maps that respect the group action.
Right, right.
The second example is a category called epid, which has to do with finite sets and surjections between them.
Okay.
And the third example is this category called vectcad, which deals with vector spaces over a field K of dimension at most D, and again, surjections between them.
So we have these categories. They all share this property of having these atomic morphisms and admitting these finite coproducts and pullbacks. Why are these categories so important for the author's goals?
Because it's in these categories that we can construct these really fascinating objects called parametrized cubes, which are essential for understanding this notion of parametrized semiadditivity that the paper is building towards.
Parametrized cubes. I'm picturing a cube that somehow depends on a parameter. Am I on the right track?
Yeah, you're on the right track. So technically speaking, a parameterized cube is an indexed product of the category AOM. That's a very basic building block in category theory.
Okay.
You can think of AO1 as the category with 2 objects. We'll call them 0 and 1.
Okay.
And a single non-identity morphism going from 0 to 1.
Okay.
So a parameterized cube is an object in a parameterized category that's built by taking multiple copies of AO1 and gluing them together in a certain way. These parameterized cubes, they're a key ingredient in the paper's construction of parameterized spheres, which ultimately play a really central role in their characterization of parameterized semiadditivity.
Okay, I'm following so far. So we have these atomic orbital categories, and we can construct these parameterized cubes inside them. What makes these cubes so special?
So the paper highlights this really crucial fact about these parameterized cubes, which is captured in proposition 3.1.14,
Okay.
which says that external indexed products of singleton co-Cartesian cubes are themselves singleton co-Cartesian.
All right, break that down for me. What are singleton co-Cartesian cubes, and what does that proposition really mean?
Okay, so a singleton co-Cartesian cube is a parameterized cube that's kind of built up from a single point.
Okay.
Think of it as like the simplest possible parameterized cube.
Right.
Now, when we take the external index product of two singleton co-Cartesian cubes, what we're doing is we're essentially combining them together in a way that's dictated by the indexing category. This proposition is saying that if we start with two singleton co-Cartesian cubes, their external indexed product is also going to be a singleton co-Cartesian cube.
Okay.
In other words, this operation of taking external indexed products preserves this property of being built up from a single point.
So it's like we're taking these really simple building blocks, these singleton co-Cartesian cubes, and we're combining them together, but in a way that preserves their simplicity.
Exactly. And this property turns out to be crucial for constructing more complex objects, like parameterized spheres.
Parameterized spheres. Now we're getting to the good stuff. Tell me more about those.
All right, so parameterized spheres are objects in a parametrized category that generalize the idea of representation spheres in equivariant homotopy theory.
Okay.
And they're constructed using these parameterized cubes we've been talking about. You essentially take a parameterized cube and you kind of collapse certain parts of it in a specific way, and what you get is a parameterized sphere.
So like taking a cube and squashing it down into a sphere.
Yeah, that's a good intuition. And these parameterized spheres are key to characterizing that idea of parameterized semiadditivity, which is a generalization of the classical Wurth-Müller isomorphism theorem in equivariant homotopy theory.
Wurth-Müller isomorphism theorem. Remind me what that is again.
So it's this fundamental result in equivariant homotopy theory for finite groups. Roughly speaking, it says that if you invert the representation spheres in the category of genuine G-spaces, that's like making them invertible, giving them inverses, then all the orbits become self-dual. It's a really powerful result with deep connections to duality in the setting.
So we're seeing these connections between these parameterized spheres and this classical result. I'm guessing Theorem B has something to do with this.
You bet. Theorem B, it essentially says that if you have a pointed parameterized category that's well-behaved, meaning it has all the limits and climits we need, and it satisfies this property called spherical invertibility, then it automatically satisfies this parameterized semiadditivity.
So spherical invertibility implies parameterized semiadditivity. Can you unpack those terms a bit?
Sure. So spherical invertibility just means that certain parameterized spheres are invertible in the category.
Yeah.
Think of it like saying that these spheres have inverses that let you undo their effect.
Okay.
Parameterized semiadditivity is a more technical condition that captures these algebraic structures in the category.
Yeah.
It's a generalization of the classical notion of semiadditivity, which is a property of categories where every object has a negative, which allows you to subtract objects.
Got it. So Theorem B says that if we have this invertibility property for certain spheres, then we get this semiadditivity property for free. That's a pretty powerful connection.
It is, and what's really neat is that the proof of Theorem B actually uses all this machinery that we've developed so far, including Theorem A and this idea of singleton excision. It's like a beautiful example of how these seemingly abstract concepts all fit together to reveal these deep mathematical structures.
This is really impressive. I'm amazed by how this paper is weaving together ideas from different areas of mathematics, from category theory to homotopy theory. It's all coming together.
Me too. And it's not over yet. The paper goes on to connect all of this to this concept of parameterized stability, which is a very central theme in this whole parameterized world.
Okay, let's dive into that. What is parameterized stability and how does it relate to everything we've discussed so far.
All right. So in ordinary category theory, a pointed category is stable if the suspension functor is an equivalence.
Okay.
This means that you can suspend an object and then you can loop it back to where you started.
Right.
It's like saying that the category is well behaved with respect to these operations.
So it's about how well suspensions and loops play together.
Exactly. Now, in the parametrized world, things get a little bit more subtle.
Okay.
So Narden, who is one of the pioneers of this theory, gave a definition of parameterized stability that involves two conditions.
Okay.
The category has to be fiber-wise stable, meaning it's stable locally, and it also has to satisfy this parameterized semiadditivity that we've been talking about.
So it's like a stricter version of stability.
Right. And this raises a really fundamental question. Can we characterize parameterized stability just in terms of some kind of invertibility of spheres like we do in the ordinary case?
That's a great question. I bet Theorem C has the answer.
You guessed it. Theorem C says that under certain presentability hypotheses, a pointed parameterized category is parameterized stable if and only if it is what we call spherically invertible.
Wow.
It's a powerful result that gives us this brand new perspective on parameterized stability.
So this paper is really tying together a lot of really deep concepts.
It does. And what's even more impressive is that the authors are hinting at future applications. They mention that Theorem C is crucial for understanding this universal property of excisive endofunctors on spectra.
So this is just the tip of the iceberg?
Exactly. We've only scratched the surface. This paper is laying the groundwork for this whole new theory of parametrized functor calculus with potential applications in lots of different areas of mathematics.
I'm so excited to see where this leads. Wow, this is incredible. It feels like we've been on like a whirlwind tour through the landscape of parametrized functor calculus.
It really has. And the paper doesn't stop there.
Right.
It kind of wraps things up on page 5 with this discussion of Theorem C and its implications, but it also leaves us with some pretty tantalizing open questions.
Before we get to those open questions, let's just take a moment to recap the major milestones of this mathematical expedition.
Yeah, let's do that. So we started by, grounding ourselves in this world of parametrized categories and functors, right?
Right.
We saw how these functors capture the idea of families of objects that vary based on this parameter.
Yeah, and then came those excisable posets, those special posets that help us break down these complex objects into simpler pieces.
Right, and it's those excisable posets that let us define that crucial concept of an excisive functor.
Right.
These are the well-behaved functors that respect certain relationships between limits and colimits.
And Theorem A, the star of page 3, gave us that recipe, right, for approximating any parameterized functor using these excisive functors.
Exactly. It's like we have this blueprint for constructing these simplified versions of complex functors.
And of course, the paper was careful to point out that technical condition of differentiability in the target category.
Oh, yeah, absolutely. That makes sure that the whole machinery runs smoothly.
All right. It's like making sure all the gears are well oiled in our mathematical machine.
Yeah.
And then we kind of enter this really fascinating realm of atomic orbital categories.
Right.
These categories where the morphisms are either isomorphisms or not. And we have these powerful tools of finite coproducts and pullbacks.
Yes, yes. And then within those categories, we encountered those intriguing parameterized cubes. These cubes, they're built by gluing together these copies of this basic category, a Hue-1, and they turned out to be the key to unlocking this whole thing about parameterized semiadditivity.
Yeah, Theorem B was pretty mind-blowing, connecting this idea of spherical invertibility to parameterized semiadditivity.
Yeah, it really tied together geometry and algebra.
And then Theorem C kind of took it even further, right, providing that new characterization of parameterized stability in terms of this spherical invertibility. It's like this, like a beacon illuminating the deeper structure of this whole parametrized world.
Exactly.
So, we've seen excision, we've seen spheres, we've seen semiadditivity, all those key ingredients that the title promised us. But as you mentioned, the journey doesn't quite end there.
Right.
Page 5 gives us some exciting future directions and open questions.
Yeah, so the paper, it highlights the importance of Theorem C for understanding the universal property of what they call decisive endofunctors on spectra, which is a topic that goes really deep into the heart of stable homotopy theory.
The excisive endofunctors on spectra. That sounds incredibly powerful. Can you shed a little light on what those are and why they're so important?
Okay. So think of spectra as like generalized spaces that allow us to capture information about homotopy groups in all dimensions,
Yeah.
all at the same time. They're like these fundamental objects in stable homotopy theory.
Right.
So a decisive endofunctor on spectra, it's a functor that takes a spectrum and sends it to another spectrum, but it does so in a way that satisfies a certain excision property.
Yep.
It's similar to what we saw with the successive functors, but it's tailored to this world of spectra. These functors capture all these important operations in stable homotopy theory, so understanding their universal property is a key step towards unraveling their deeper structure.
So this paper is not only giving us this framework for parameterized functor calculus, but it's paving the way for new discoveries in stable homotopy theory as well.
Right,
It
exactly.
feels like we're standing at the edge of a vast uncharted territory.
Absolutely, and that's what makes this paper so exciting. It's not just about proving these theorems, it's about opening up new avenues of research, asking these new questions, and really pushing the boundaries of our mathematical understanding.
The paper mentions a forthcoming work that will explore the universal property of these decisive endofunctors in more detail. What kind of questions do you think they'll be tackling in that work?
Well, I think one of the central questions is going to be, what's the best way to approximate a given endofunctor on spectra using these decisive endofunctors?
Okay.
Theorem A gave us a really beautiful answer to that question in the context of parametrized functors, but the world of spectra is much richer and much more complex. Finding a similar result in that setting would be huge.
It's like we're taking the blueprint provided by Theorem A and trying to adapt it to this more intricate world of spectra.
Yeah, that's a great way to put it. Another question that they might explore is how these de-excisive endofunctors interact with other important structures in stable homotopy theory, like smash products and localization. Understanding those interactions would give us deep insights into the algebraic and geometric properties of these functors.
It sounds like there's this whole web of interconnected ideas waiting to be explored.
Absolutely. And this paper has given us the tools and the inspiration to start weaving that web.
This has been a truly mind-expanding deep dive. From the foundations of parameterized categories to the frontiers of stable homotopy theory, this paper has taken us on a remarkable journey.
It really has. And it's clear that this is just the beginning. I'm excited to see what new discoveries and connections emerge from this work.
Me too. A huge thank you to all our listeners for joining us on this adventure into the heart of cutting-edge mathematics. We encourage you to check out the source material and see what insights you can find. Who knows, you might be the one to make the next big discovery in this exciting new field.
Absolutely. Until next time, keep those mathematical minds sharp.
And never stop exploring. Welcome to another deep dive. Today we'll be exploring a paper all about parameterized functor calculus. I think you'll find it quite fascinating.
Oh, this sounds very interesting.
It is. It's by Kaif, Hilman, and Linskens.
Oh, okay.
The title is Parametrized Functor Calculus, Excision, Spheres, and Semiadditivity.
I've been meaning to take a look at this one.
Oh, cool.
What's the main idea?
Well, they're building this whole theory of parameterized functor calculus based on Goodwillie's work, and they apply it to better understand parametrized semiadditivity.
Okay.
And what's really neat is that there's this connection they uncover between invertibility of certain parametrized spheres and the concept of semiadditivity.
Oh, that sounds interesting, like a generalization of the classic result in equivariant homotopy theory about the invertibility of representation spheres.
Yeah, exactly, but in a much broader setting.
Okay, exciting. So how do we start?
Well, how about we start with the basic building blocks?
Okay.
What are those?
Excisable posets. Yeah, they're sort of special partially ordered sets with some nice properties.
Okay.
The authors emphasize the Boolean nature of these posets, which allows for a clean approach to breaking them down, analyzing their structure.
Okay, and then that leads into Theorem A,
Right, yeah.
The one of the core results.
The core result.
What
Theorem A says that under certain conditions, we have a special relationship between all functors, and then this subset of them called the excisive functors.
Okay.
And there's this way to go back and forth between these two collections using what's called a left adjoint.
Right.
And what's really important is that this left adjoint, it has this explicit formula.
I'm guessing that's important later on?
Oh, yeah, very important. It plays a key role in the applications.
Okay.
Specifically when they start looking at atomic orbital categories.
Okay, so things are starting to get a little bit more concrete here. What are these atomic orbital categories?
Yeah, so they're a special type of category that captures, certain notions of symmetry, like with orbits.
Okay.
Yeah, and within these categories, they introduce parametrized cubes, which are specific examples of our good old excisable posets.
Right.
So these cubes, they're, higher dimensional versions of squares, and they play a similar role to, the familiar n cubes you see in Goodwillie calculus.
So we've got these cubes, which are made of excisable posets. What happens next?
Well, then they use these cubes to define parametrized spheres, which are, analogous to regular representation spheres in this setting.
Okay.
And this is where Theorem B enters the picture.
All right.
Yeah, it establishes this powerful link between something called spherical faithfulness and the concept of semiadditivity within a locally short atomic orbital category.
Okay, spherical faithfulness, what is that?
Yeah, so it essentially means that certain functors, I think they're called suspension functors, behave nicely when you apply them along these parametrized cubes.
Okay.
They preserve all the information, so to speak.
Got it.
So Theorem B tells us that in this setting, if you have spherical faithfulness, you also get semiadditivity for free.
Wow, that's pretty cool.
Yeah.
So I bet the explicit formula from Theorem A is helpful here,
Yeah,
right?
yeah, absolutely.
When you're proving Theorem B.
Exactly. It's a beautiful example of how the theoretical groundwork they lay out really pays off when they get to these applications.
All right, I think I'm following so far.
Good.
Excitable posets, parametrized cubes and spheres.
Yes.
This connection between spherical faithfulness and semiadditivity. Anything else we should know before we dive into the math?
Yeah, there's one more piece to the puzzle.
Okay.
Narden's definition of parameterized stability.
Okay.
So this definition, it seems to separate out two conditions.
Okay.
So, it leads to this natural question. Is there a more concise way to characterize parameterized stability? Right.
And Theorem C comes to the rescue.
It seems like these theorems always show up right when we need them.
They do, yeah.
So what does Theorem C tell us?
It states that in a suitable setting, parameterized stability is equivalent to something called spherical invertibility.
Okay.
So this means that our suspension functors along these parameterized cubes, they're not just faithful, but they're invertible in a sense.
Right.
Yeah, it's a really nice way to capture the essence of parametrized stability.
Nice. So we've got the big picture now with all the key players and all the connections. I think I'm ready to roll up my sleeves and dive into the math itself.
Great. Yeah.
So let's start with those excisable posets you mentioned. What exactly are they and how do they work?
Good question.
Yeah.
Yeah, so they start by defining a parameterized poset as an object in poset toki, fun top poset ket.
Okay, so we're already in category theory. Can you just unpack those symbols a little bit for me? Yeah, of course. So poset, that's the category of partially ordered sets.
Okay.
And T is just an arbitrary category.
Got it.
And then fun top poset, that represents the category of functors from the opposite category, T to poset. And cat T is the category of categories enriched over T.
Okay.
So basically a parameterized poset, it's like a functor that assigns a poset to each object in T.
Gotcha. So these parameterized posets give us a way to kind of like vary our posets over different objects.
Okay, yeah.
Okay, so what makes a parameterized poset distributive?
So a parameterized poset is distributive if it has finite products and coproducts fiber-wise. We write for products and for the coproducts.
Okay.
And they need to satisfy a specific condition.
Okay.
Yeah. So the natural map C must be an equivalence.
Right.
This ensures that the product and coproduct operations distribute over each other, consistently across different objects in T.
Right, distributivity.
Yeah.
So familiar from algebra, but now we're seeing it in this categorical setting.
Exactly, yeah.
What about initial and final objects in these parameterized posets?
Yeah, so we denote the initial object as A and the final object as 1, as usual.
Yeah, makes sense. Now, how do we know if a parameterized poset is complementable?
So a parameterized poset is complementable if for every object A there's another object, AC. You can think of it as the complement of A,
Okay.
such that two conditions hold.
Right.
First, a AAA1,
Okay.
and second, a DC.
Got it. So every object has a complement that, when you combine it with the original object, either using the coproduct or the product, gives you either the final object or the initial object.
Exactly, yeah.
It's interesting how these very familiar concepts from like basic set theory complements, unions, intersections, are showing up in this abstract world of categories and functors.
Yeah, it's really neat.
Yeah.
Yeah, and then they remind us of a few crucial facts. First, that coproducts are pushouts in posets.
Okay.
Second, that products are pullbacks in posets.
Okay.
And so what this means is for a finite set S in posets, that's the poset of subsets, coproducts correspond to unions and products correspond to intersections.
Okay.
Yeah.
Okay, I'm with you so far. We've got these parameterized posets, and we know what it means for them to be distributive and complementable. What's next?
Yeah, so they list a few useful properties, assuming, of course, that the necessary coproducts exist.
Right.
First, that XO pos.
Okay.
Second, that XX.
Okay.
Third, that XX.
Okay.
Fourth, that XX.
Okay.
And fifth, that XX.
It's very reminiscent of what we see with set operations like union and intersection.
Exactly.
Yeah.
Yeah. And then focusing on complementable posets, they introduced the concept of smashing supposets.
Okay.
Yeah, so for L, a complementable poset, and XL, an element of L, LX denotes the full subcategory spanned by the image of the functor SSO.
Okay, so LX is essentially all the elements in L that you can get by smashing something with X using the product operation.
Exactly.
Okay, so what are some key properties of these smashing supposets?
Yeah, so a few.
Okay.
First, LX has an initial object, L, and a final object, X.
Yeah.
Second, it inherits distributivity from L.
Okay.
So the same distributive laws hold within LX.
Got it.
Third, it's also complementable.
Okay.
So every element in LX has a complement
Okay.
within LX.
Okay.
And fourth, it's downward closed in L.
Right.
Meaning if Y is an element of LX and ZAY, then Z must also be in LX.
So they retain a lot of the structure of the original poset.
Exactly.
What can we do with them?
Well, they lead to a nice decomposition of the original poset.
Okay.
Specifically, the functors, LXS-LX and LXLC, are inverse equivalences.
Okay, hold on. Let me just make sure I'm following.
All right.
So we're taking our poset L, and we're breaking it down into these two pieces, LX and LXE.
Right.
And the first functor takes an element of L and maps it to a pair of elements, one in each of these supposets. And then the second functor takes a pair of elements, one from each, and combines them back into an element of L.
Yeah.
And you're saying these two functors are inverses of each other? So they essentially undo each other's actions?
Exactly, yeah. It's like taking a puzzle apart and putting it back together.
Okay.
Yeah. So this decomposition, it's a really powerful tool because it allows us to analyze the structure of L by studying these simpler supposets, LX and LXC.
I can see how that would be useful.
Yeah. And there are a few consequences of this decomposition.
Okay.
First, we get these things called boost field localizations.
Okay.
So LX right arrow, LX with right adjoint arrow, and then LX right arrow XC with right adjoint apple.
Right, Bell's field localizations. They're like putting on a pair of glasses that let you see certain aspects of the poset more clearly.
Exactly, yeah. Great analogy.
And then another useful property is that for L complementable in XL, the functor ESA,
Yeah.
LEL has a left adjoint XA.
Right.
So there's this back and forth between smashing with X and taking the coproduct with X.
Exactly, yeah.
Okay, so we've covered a lot of ground with these complementable posets and their properties.
Mm-hmm.
But I'm still a little bit fuzzy on like the main star of the show, excisable posets.
Right.
What makes them so special?
Yeah. So an excisable poset consists of, well, first a complementable poset, L poset T.
Okay.
And then a non-empty, downward closed, full supposet poset.
Okay.
Note that L must contain an initial object.
Got it.
Yeah. So think of L as the special substructure within L
Okay.
that allows us to define a notion of excision.
Okay, so I'm starting to get the picture. We have this bigger poset L, and then we've got this carefully chosen supposed L sitting inside it.
Exactly.
Okay. So what kind of results do we get when we have these excisable posets?
Yeah, so they prove a series of lemmas
Okay.
that highlight the interplay between the poset L, the supposit L, and the elements within them.
Okay.
For example, they show that for L complementable, XL and LLL downward closed, the image of the functor X right taro XO LX,
Okay.
we denote it LSLX,
Got it.
is also downward closed.
So if we take our special supposit and we smash it with an element, the resulting set of elements is still downward closed.
Exactly.
Okay. What other constructions did they introduce?
Yeah, so they define LAL as the full supposit, excluding the initial object,
Okay.
and then LA as the inclusion of the initial object.
Okay.
So you can think of these as ways to focus on different parts of the poset, right? Like the non-initial elements of L and then the initial object itself.
Okay.
And they use these to define different types of diagrams within L.
Okay, cool. So we've got posets, we've got supposits, we've got these different constructions that let us focus on different parts of the poset.
Yeah.
What about functors between categories? How do they fit into the picture?
Right. So that's where the concept of ignoranceability comes in.
Okay.
Yeah. So for a functor FIU between categories and a category C or sket T, C is said to be F left extensible or F right extensible if left or right. Can extensions along F exist in C?
So extensibility is about whether or not we can sort of like stretch functors in a way that's consistent with the categories.
Exactly, yeah.
Okay.
So then they use this to define special types of diagrams.
Okay.
Yeah, so a diagram D, fun, LL,
Okay.
is said to be co-Cartesian if it's in the image of wolfun, fun LC.
Okay.
And it's Cartesian if it's in the image of fun LC. We denote these categories of diagrams as funsus and funcart.
Okay. So a Cartesian diagram is basically a diagram that comes from a diagram in the supposit.
Right, exactly.
And then a Cartesian diagram comes from the supposit that excludes the initial object.
Exactly.
Okay. It seems like we're building up to a definition of excision based on how these diagrams interact.
Yeah, exactly. And they prove this crucial result.
Okay.
For a co-Cartesian diagram, DUA, fun LC, and an element X.
Okay.
The functor LC is also SCO-Cartesian.
Wait, hold on a second. What exactly is that functor DLC doing?
Right. So it's taking an element Y of L,
Okay.
combining it with X, using the coproduct,
Right.
and then applying the original diagram D.
Gotcha. Okay. And so you're saying if D is a SCO-Cartesian, then this new diagram is also SO-Cartesian.
Exactly. So this result shows how, the structure of these diagrams interact with the coproduct operation. Yeah, and then they prove a similar result for Cartesian diagrams.
Okay.
But first they show that for categories P, I, C, S, C, cat, with P and I having initial objects,
Right.
I having a non-initial final object, and C having the necessary can extensions.
Okay.
The diagram F, PX right, CC is Cartesian for any functor FPC.
Okay. So under certain conditions, this composite diagram is always Cartesian.
Exactly, yeah. And so building on this, they show that for C-T, an excisable poset, and XAOL,
Okay.
the diagram D is Cartesian for any DLSC.
Okay.
So instead of the coproduct, now we're focusing on diagrams built using the functor.
Right. Okay.
And just like before, if the original diagram is Cartesian, then this new diagram is also Cartesian.
Okay. I'm starting to see the patterns here. We're establishing how these special types of diagrams behave when we combine them with certain functors.
Exactly.
Involving the coproduct or like taking an element and smashing it with other elements.
Right. And these results are really important for their main results on excision.
Okay.
But before we get there, we need to take a little detour
Okay.
and explore the concept of face decomposition.
The decompositions.
Yeah, which play a key role in analyzing the structure of these diagrams.
Sounds intriguing.
Yeah. So they start by defining two elements, A, DL, in a complementable poset to be disjoint if it A is.
Okay.
This simply means that their product is the initial object.
So disjoint elements are kind of like orthogonal elements in a vector space. They don't overlap in any way.
Yeah, that's a good intuition.
Okay.
Yeah, and then three elements, A, D, A, L, they form a decomposition of L
Okay.
if they are pairwise disjoint. and 80 as x1.
So decomposition is like partitioning L into 3 slices
Exactly.
that cover the entire posit.
Right. It's like cutting a cake into 3 pieces.
Okay.
Yeah.
So what do we do with these decompositions?
Yeah, so we use them to define face posets. Yeah, so for a decomposition ADZL, they define the A face as the fully faithful functor.
LA X-right error Z. LA X-right error Z, Ln E Z.
Wow, that's quite a chain of functors.
It is, yeah.
So what's the intuition behind this A face construction?
Right. So it's a way to focus on the part of L that sort of interacts with the element A.
Okay.
Right. So we start with the smashing supposit LA,
Okay.
which captures all elements that you can obtain by, smashing something with S.
Right.
And then we map this into the larger smashing supposit as A using the functor A.
Okay.
Next, we sort of shift this supposit using the functor.
Okay.
And finally, we map everything back into L using...
Okay. So we're zooming in on the part of L related to A, and then we're embedding it back into the original posit.
Exactly.
Okay.
Yeah, and given an excisable structure,
Yeah.
LAL, we can induce an excisable structure cell
Huh.
by setting L as the image of LA extra to LA.
So we're taking a smaller slice of our excisable posit.
Right.
Okay. So what else do they do with these face posets?
Yeah, so they define these categories, I and J, via these Kullback squares.
Okay.
IX art LA and J X art LA from L caro L and L LA respectively.
Right. So it's like we're taking different pieces of the posit and fitting them together in this very specific way based on the decomposition.
Exactly.
Yeah.
And this construction yields a functor day A, LALD, which is part of a boost field colocalization.
Yeah.
LA, right left arrows, LD.
Right. So we're back to Bosefield localizations. Seems like they're everywhere.
They are, yeah. They're really useful for focusing on specific parts of the posit.
Okay.
Yeah. And then they prove a couple key results using these phase posits. First, they showed that for a parametrized cocomplete category C, an excisable posit LEL and LL, if the diagram X, LEC is co-Cartesian,
Okay.
then every A face of X is co-Cartesian.
Okay. So the property of being so Cartesian is preserved when we focus on the A face of the posit.
Right.
Okay.
And additionally, they show that if every A face of a diagram X, LEC, is Cartesian, then X itself is Cartesian, given that C is parametrized cocomplete and L is a complementable parametrized posit.
So if all the slices of the diagram are Cartesian, then the whole diagram must be Cartesian.
Exactly. Yeah. It makes intuitive sense.
Yeah.
And so we're finally ready to tackle the concept of excision itself.
Okay. I've been waiting for this. How do they define excision in this setting?
Right. So a functor FCEAD, where C is left extensible and D is right extensible, is successive if it sends co-Cartesian diagrams to Cartesian ones.
Okay.
So this means that the following diagram in cat T admits a dashed factorization. Fun LC, fun LC, fun LC, fun LC.
Okay.
And then the full subcategory of successive functors in fun CD is denoted XCD.
Okay.
So basically, a successive functor excises the part of the diagram that comes from the initial object of A.
Okay. So if we have a diagram that's built from a diagram in the supposit, a successive functor transforms it into a diagram that looks like it came from the supposit that excludes the initial object.
Exactly. It's like cutting out the part of the diagram related to the initial object.
Okay.
Yeah. And then a category D is differentiable if it has sequential colimits and Lin-indexed limits that commute.
Okay.
So this condition ensures that certain limit and colimit operations play nicely within D.
Right. Differentiability. So it's like saying that certain operations in D are behaving smoothly and continuously.
Exactly, yeah.
Okay.
Okay, so to understand how to approximate an arbitrary functor by a successive functor, they introduced the excisive approximation functor. So assuming C has a final object, they define T, fun CD. Fun CD as the composite. Fun CD, X right arrows to fun CD, where C is the composite C, X right arrows funny.
Okay.
And this T, it comes with a natural transformation, CD T.
Okay. I'm going to need a moment to unpack that. That's quite a complex construction.
It is, yeah. So let's break it down step by step.
Okay.
So we start with an arbitrary functor, FCD. So the first step, represented by L, is a way to lift F to a functor between categories of diagrams indexed by L.
Okay.
The second step, C, takes a diagram in C indexed by L, and it transforms it into a co-Cartesian diagram.
Okay.
So like restricting it to the supposed and then extending it back to L.
Okay.
And then the third step, CDK, it cuts out the part of the diagram related to the part of the diagram related to the initial object of L.
Okay.
So the composite functor T takes our original functor F and sort of forces it to behave like a successive functor on Cartesian diagrams.
Okay, I'm starting to see the light. It's like we're taking our functor and molding it into something that's closer to being successive.
Yeah, exactly. And then the natural transformation, KAV, is a way to compare the original functor with this, molded version.
Okay. So we've got this functional cheese that gives us this rough approximation of a successive functor. How do we refine that approximation?
Yeah, so that's where the successive approximation functor piece comes in.
Okay.
So assuming C has final objects and D has sequential colimits, the excisive approximation functor piece on CT is defined as piece in, column piece, column id, x reiterates.
Okay.
So this construction is essentially taking the colimit of a sequence of functors,
Okay.
each of which is obtained by applying t's repeatedly.
So we're iteratively applying t's to get like a better and better approximation of a successive functor.
Exactly, yeah. It's like refining a sculpture. You chisel away at it bit by bit.
I like that. What kind of results do we get when we use this Pice functor?
Yeah, so they prove a series of lemmas
Okay.
leading to their main theorem about excisive boost field localization.
Okay.
For example, they show that for categories C, D, cat T with final objects where C is left extensible and D is so right extensible.
Okay.
Given a functor FCD and a co-Cartesian diagram DLEC, the canonical map B, FD factors as FDE at Ishi with Ishi Funcart LD.
Okay. So we're starting to see how all these different pieces fit together.
Yeah, it's all about building up the machinery for their main result.
Okay.
Yeah, so then they prove that for category CD, GAT T with final objects, C being left extensible and D being right extensible, the functor PF. CD is excisive for any functor FCD.
Okay, so this means that PC actually does what we want it to do. It takes an arbitrary functor and produces a successive functor. All right, that's pretty key. What else do we know about POS?
Yeah, so they also show that these approximations are idempotent.
Okay.
Yeah, so for category CDAD key with final objects, C being left extensible and D being differentiable, the transformation C is PSF, is an equivalence for any FCD.
Okay.
And what this implies is that applying piece twice is the same as applying it once.
So once we've approximated a functor, applying piece again doesn't change anything.
Exactly, yeah. It's like saying that your sculpture is already as refined as it can be.
Right, okay.
Yeah, and so with all these results in place, they finally get to their main result about excisive Bose field localization.
Okay.
So for an excisable poset, left L with C having a final object and D being differentiable, the inclusion exte suc, passive on CD, admits a left adjoint to pace. If D has finite parametrized limits that commute with sequential colimits, then piece is parametrized left exact.
Whoa, okay, that's a lot. Can you break that down a little bit?
Yeah, so first, the inclusion excisiveness sopum it just means we're viewing the category of successive functors as a subcategory of the category all functors.
Okay.
From C to D. And then the statement that this inclusion admits a left adjoint paris means that there's a way to go back and forth between these two categories using paris.
Right.
In other words, paris, it gives a best approximation of an arbitrary functor.
Okay.
By a successive functor.
Okay.
Yeah, and then the additional condition about finite parameterized limits that just ensures that PES preserves certain limits.
Right.
Which is, a desirable property.
Okay, great. So we've built this whole machinery for approximating functors by successive ones.
Right.
What's next?
Yeah, so to wrap up their discussion of excisable posets, they prove this useful result about the relationship between excisiveness and sec-excisiveness. Yeah, so they show that for an excisable poset, L, and a successive functor, FCD, F is also successive.
Okay, so If a functor is excisive when restricted to the A face of L, then it's excisive on the whole poset L.
Exactly, yeah. If it can excise the initial object on a smaller piece, it can do it on the whole thing.
Got it. So are there any interesting consequences of that result?
Yeah, so it leads to the observation that given a sequence of excisable posets with objects, AA, AI, AI, AAA, such that CAA plus 1, AI plus 1, we obtain a Goodwillie tower A, perio A, associated to this sequence.
So we've gone from these very abstract excisable posets to these very concrete Goodwillie towers.
Right, it's really cool.
That's awesome. All right, so that concludes our exploration of excisable posets.
Yeah.
Where do we go from here?
All right, so now that we have a good understanding of the foundational concepts, we can move on to the exciting part.
Okay.
Applying this theory in the context of parameterized cubical excision. This is where, those parametrized cubes and spheres we talked about earlier really come into play.
Okay, I'm ready to see how these cubes fit into the picture.
All right, so let's delve into the world of parameterized cubical excision.
Okay.
Remember those atomic orbital categories we touched upon earlier?
Mm-hmm.
They're crucial here.
Okay.
So just to refresh our memory, atomic orbital category, T has the property that any morphism FWV and GV, FW and T, satisfying G, S being an equivalent, implies that both F and G are already inverse equivalences. Additionally, T is orbital if its finite co-completion, fin T, admits finite pullbacks.
Right, atomic orbital categories, they capture certain symmetry related to orbits.
Exactly.
Yeah. So how do we connect these categories to the idea of cubes?
Right, so for morphism WWV and fin T and a T category C, the parametrized W cube is defined as the TV category W1.
Okay.
And then a parametrized W cube in C is then a TV functor Q, WG1VC.
Okay, let me unpack that. So we have this morphism W in our atomic orbital category.
Yeah.
We're using it to build this special category Y1, which we're calling a parameterized cube.
Right.
And then a parameterized cube in C is just a functor from this cube category into another category related to C.
Exactly. And these parameterized cubes, W1,
Okay.
they have this peculiar characteristic.
Okay.
Their only global points are the initial and final objects.
Okay, global points. Can you expand on that a little?
Yeah, so a global point of a category over T is simply a section of the structure map.
Okay.
In this case, a global point of W1 would be a map T, on len in cat, such that the composite T W1 is the identity.
Okay.
But due to the junction between W and the forgetful functor, such a map corresponds to a map T1 in cat.
Okay.
And since U1 only has two objects, 0 and 1, the only possible global points of W1 are those corresponding to these objects.
So because of the way that these parameterized cubes are constructed, the only points that sort of like live over the final object of T are the initial and final objects of the cube.
Exactly, yeah.
What about the other points?
Right, so the other parameterized points, they come from B points B, DOR1,
Okay.
where IV is the unique map in TV, and B is not the final object.
Okay.
So these points, they capture the local structure of the cube over different objects in T.
So these B points give us a way to sort of like zoom in on the cube over a specific object B.
Exactly.
Can you give us a more concrete picture of what these B points look like?
Yeah, so let's consider this simplified scenario.
Okay.
Where T has a final object, V, and WWEV is the unique map to V.
Okay.
So then a B point YB for BT and BBV can be visualized as a selection of orbits in the decomposition of BWE1, A into orbits over B.
Orbits. So now we're really tapping into the symmetry aspects of these atomic orbital categories.
Yeah, exactly.
Okay.
Yeah, so this decomposition reflects how the object W sort of breaks up into smaller pieces when you view it from the perspective of B.
Got it.
And then the B point Y, it essentially picks out specific orbits from this decomposition.
Okay, I'm starting to see how the picture is coming together, but can you explain how exactly a B point corresponds to a selection of orbits?
Right, so by adjunction, the B point Y corresponds to a map, Abioboy1, X, U, ear, AU, Yago, where UI, UIE, B are the structure maps of the orbits. And this map, it's determined by maps U1, U111, each of which is either the constant functor at 0 or 1.
Okay.
So choosing 1 for a specific I corresponds to selecting the orbit UI.
So the B point is encoding a binary choice for each orbit.
Exactly, yeah.
Select it or don't select it?
Yeah.
Okay.
So this gives us a concrete way to visualize these B points as selections of orbits.
Okay.
Yeah. Now, let's move on to a crucial construction.
Okay.
The singleton inclusion map, denoted as TOB1.
All right.
And this plays a vital role in generalizing Goodwillie's notion of strong co-Cartesianness to this parameterized setting.
Okay. So singleton inclusion, what's the intuition behind that?
Yeah, so it generalizes the idea of including subsets of size at most 1.
Okay.
In an ordinary cube. So remember, in Goodwillie's calculus, strong co-Cartesianness involves considering squares, where the value at the top right corner is determined by the values at the other 3 corners.
Right.
Right. And so the singleton inclusion map, it captures this similar idea in this parameterized setting.
So it's about extending information from a smaller part of the cube to the whole cube.
Exactly, yeah.
How is this map actually constructed?
Right. So it's built in 2 steps.
Okay.
First, we construct a maps for WAU1.
Okay.
To do this, we utilize this special pullback diagram that arises from the atomic orbital structure. So we have this pullback, W your C into UW your V, where C is an object in fin T.
So this pullback is capturing some information about the relationship between W and V in our atomic orbital category.
Exactly.
Okay.
And so this pullback, it gives us a decomposition fin to 1, S ET1, where CTV is the map from the pullback.
Okay.
And then the map W. SAU1 is then defined using this decomposition.
Okay.
So we set the map, APO1 is the inclusion of the target, UF1, and the map, SC applied to the inclusion of the source.
So we're taking this decomposition of WU1 and we're using it to define a map that essentially picks out a specific point in the cube.
Exactly, yeah.
Okay.
And this point represents a singleton.
Okay.
A point that's determined by a single element.
Right.
And then this map,
Yeah.
it induces the desired singleton inclusion map, WO1.
So C is kind of like the blueprint for building the singleton inclusion map. Okay. What are some key properties of this map?
Yeah, so importantly, the shoe is stable under base change and fully faithful.
Okay.
So this means that for a map BBB, V in T, the base change of W along B, denoted as WPWB, satisfies PF. And then full faithfulness, it just means that the map foo, it preserves all the information.
Right. It's like saying it's a injective in a categorical sense.
Exactly.
Okay.
Yeah, so we have this singleton inclusion map, and it behaves nicely when we change our perspective within the category.
Yeah.
So how do we use this to define spatial types of cubes?
Right.
So we use it to define the notions of singleton co-Cartesian and singleton Cartesian cubes.
Okay.
So a parametrized cube is called singleton co-Cartesian if it can be obtained by left can extending from the singletons.
Okay.
This is equivalent to being so co-Cartesian.
Okay.
Meaning it's built by sort of gluing together singleton cubes along the map. And similarly, a cube is singleton Cartesian if it's right can extended along W or up, X right for a lop.
So these singleton co-Cartesian and Cartesian cubes, they're built by kind of assembling these singleton cubes in specific ways.
Exactly. They're like Lego structures made from these fundamental building blocks.
I like that.
Yeah. And it turns out that these singleton co-Cartesian cubes, they have this nice property.
Okay.
The external index product of a singleton co-Cartesian cube is also singleton co-Cartesian.
Okay. External indexed products. What are those?
Right. So they're a way to combine diagrams in a way that respects the structure of our base category, T.
Okay.
So for a map AV A in T and categories IC, QOTV,
Okay.
there's a natural map, funI, AC, AI, AC.
Okay.
So this map, it essentially takes a diagram X, IAC, and produces a new diagram, AX equals AI, AKAC.
So we're taking a diagram over V and we're pushing it forward along the map A to get a new diagram over A. Okay. So how is this map defined?
Yeah, so it's defined using the adjunction countit, ADRAI.
Okay.
So we first obtain a map, fun IC, X right, R fun AIC.
Okay.
Applying A to this map and using the equivalence, a fun AIA, fun AIAC, yields the desired map, a fun IC, fun AI AC.
Okay. It seems like we're using the adjunction between A and its right adjoint to sort of transfer the diagram from I to AI.
Exactly.
Okay.
And if I has an initial object, then the atomicity of T implies that AAIIA is simply the projection
Okay.
onto the I component in the decomposition AIAIAICCI.
Okay.
And this decomposition, it arises from the fact that VAAVAC.
Okay.
And since CCI has an initial object, we have an adjunction-rejection, CCI.
Okay.
And taking the product with I yields AIIA.
So in the case where I has an initial object, this map is essentially just projecting onto a specific component of a decomposition.
Exactly. And this property, it makes these external index products, particularly well behaved.
Okay.
Yeah. So let's consider a functor JIE
Okay.
that preserves the initial object.
Okay.
Then we can show that the following square commutes.
Okay.
A fun EJC, X right arrow fun AEC.
A fun JC, X right arrow fun, AE, AC, where the vertical arrows are given by AEJ.
So this square is telling us that taking the external indexed product is compatible with applying functors that preserve initial objects.
Exactly.
Okay. So how does this relate to that observation about singleton co-Cartesian cubes?
Yeah, so this commutativity property, it's crucial for proving that indexed products preserve singleton co-Cartesian cubes.
Okay.
To see why, we need to delve into this concept of push forward of singletons.
Push forward of singletons, okay.
Yeah. So given maps WWV infinity and AVAAAT, we aim to factorize the map AJJ from construction 3.1.11.
So we want to express it as W. Ace hero is W. Ace here WA, AAW, where C is the junction unit, and A is the unique map making the triangle commute.
Okay, so we're breaking down this map into two simpler maps.
Yeah.
What's special about this map?
Right. So the key observation is that the composite AW A squared A3 is equivalent to Fa.
Okay.
And this can be proven by showing that the composite AW X right AW, which preserves the initial object, is equivalent to the singleton inclusion map. So
Okay.
this proof involves utilizing the orbital decomposition V AAAC and demonstrating that the data defining this composite map is the same as the data defining for AAW AA1.
Okay.
Yeah. And so the upshot is that external index products, they indeed preserve singleton co-Cartesian cubes.
All right, so how does that work?
Yeah. So let's say we have a singleton co-Cartesian W cube, XW on 1, AC, and a map AVA in T.
Okay.
Then AX on 1 AAC is a singleton co-Cartesian A cube.
Okay.
So the proof involves constructing this large commutative diagram using the triangle from construction 3.1.13, the square from proposition 3.1.12, and the fact that the composite of the right vertical arrows is equivalent to the bent arrow.
So by carefully analyzing all these interactions between these maps and these diagrams, we can establish this preservation property.
Exactly.
It's amazing how everything fits together.
Yeah, this result highlights, the power of working with these parameterized cubes in their associated constructions.
Okay.
Yeah. Now, let's shift our focus to the construction of parametrized suspension in loop functors and the parametrized spheres.
Okay, I'm excited to learn more about those. What are they exactly?
Right. So let's assume C is a parametrized co-complete category
Okay.
with a final object.
Yep.
Then for a map WWV infint with Tror, denoting the inclusion of the initial object, the parametrized suspension endofunctor, L on C, is defined as the composite of TV functors. VC X right low and Y1, VC S right colon VC.
Okay, let me break that down. So we're starting with the category VC,
Right.
which consists of objects in C over V.
Yes.
And then we're using the inclusion of the initial object in EOR to map into a category of functors.
Right.
And then finally, we're taking the colimit of these functors to get back to VC.
Exactly.
Okay.
Yeah, so this composite functor is the parameterized suspension endofunctor.
Okay.
It essentially suspends an object over V by considering how it interacts with the initial object of the cube W1.
Got it. So what about the parametrized loop endofunctor?
Yeah, so if C is also pointed and parametrized complete, the parametrized loop endofunctor is defined as the composite of TV functors.
VC, X right taro lim VC.
So this time, instead of the initial object, we're using the final object
Okay.
of the cube W1 and we're taking the limit instead of the limit.
So it's kind of like the dual construction to the suspension functor?
Exactly.
Okay.
Yeah, and in the specific case where CS, the W parametrized sphere is defined as SWA, can S 0S.
Okay.
And this object, SW fun TV op, it's fiber-wise given by spheres of different dimensions.
Spheres of different dimensions. Can you explain that?
Yeah. So remember that wheel one is fiber-wise given by punctured cubes. So applying proposition 3.2.1, we see that SW is fiber-wise given by a suspension of S0.
Okay.
And since the dimension of the sphere obtained by suspending S01 times is n, and the fibers of one are punctured cubes of varying dimensions, SW is fiber-wise given by spheres of different dimensions.
Ah, that makes sense. So these parametrized spheres, they capture the multidimensional nature of these parameterized cubes. Okay. And as you might expect, the suspension and loop functors form an adjunction.
Right.
So for an atomic orbital T, a morphism WWV infinity, and a pointed parametrized bicomplete category C, we have the following adjunction. EC, VC,
right.
adjunctions. They're like the yin and yang of category theory. They always show up in these pairs.
Yeah, that's a good way to put it.
Okay.
Yeah. And based on these suspension and loop functors, we can define two important properties of categories.
Okay.
Spherical faithfulness and spherical invertibility.
Okay, I'm intrigued. Expert.
Spherical faithfulness and spherical invertibility.
Okay, so what do those properties tell us about a category?
Right. So let C be a pointed, parametrized by a complete category.
Okay.
And let W or V be a morphism in fin T.
Okay.
So we say that C is
okay.
1, W spherically faithful if the endofunctor is V.
Yeah.
C of TV categories is fully faithful. And she commutes with sequential colimits. And 2, W spherically invertible if the endofunctor VCEC of TV categories is an equivalence.
Okay.
If these properties hold for all morphisms WWV and FINT, then C is simply called spherically faithful or spherically invertible, respectively.
So W spherical faithfulness means that the suspension functor along W doesn't lose any information.
Right.
And the loop functor behaves nicely with colimits.
Exactly.
And then W spherical invertibility means that the suspension functor along W is essentially an isomorphism.
Right.
We can go back and forth without losing any information.
Yeah, so these properties capture how well-behaved the suspension and loop functors are along a specific morphism, W.
Got it.
Yeah.
Can you give us some examples of categories that are spherically faithful or invertible?
Yeah, so let's consider the case T for a finite group G.
Okay.
And the map WWV being the unique map GHEGG in OG.
Right. Yeah.
So in this case, the suspension is given by S star G, where rho G is the reduced permutation representation.
Got it.
So pointed, parametrized by complete category C, equipped with a symmetric monoidal structure that preserves parametrized colimits in each variable, is W spherically invertible if the object SW, W1 civ is invertible.
Okay.
And this follows from the fact that SW on C. And since SW is an automorphism, so is W1.
So in this specific case, spherical invertibility is determined by the invertibility of a particular object.
Right.
The W parametrized sphere.
Exactly. So this example highlights the close connection between these parametrized spheres and the properties of spherical faithfulness and invertibility.
Yeah, it's neat how these abstract categorical concepts can be manifested in these concrete examples.
Yeah, it is.
Okay, so how can we manipulate these spheres?
Right, so it turns out we can develop a sort of calculus for them.
Calculus for spheres, that's exciting.
Yeah, so let C be a pointed to co-complete category, and let U, UV, and WWV be maps in FINT.
Okay.
And then denote by W rho plus the map WV X right arrow V.
Oh, right.
So then the following hold.
Okay.
1 plus rho U, VC.
Yeah.
2, W Eva Wicho. VC V specifically, V plus rho plus VC. And 3, Evo plus 1 plus rho. Here the T-symmetric nodal structure on S comes from the equivalence ever as S.
Okay, let me try to parse those equations. The first one is saying that suspending along W plus is the same as suspending twice along W.
Right.
The second one says that suspending along the coproduct of U and W is the same as suspending along U plus and then along W plus.
Right.
And the third one relates the external tensor product of W with the sphere S1 to the sphere SW plus.
Exactly.
So these equations give us a way to manipulate and relate these spheres. They're like forming the basis of this calculus for understanding how suspensions behave in this parameterized setting.
Exactly, yeah.
It's amazing how these abstract objects can be manipulated using equations, just like numbers or functions.
Yeah, it's really cool.
So now I'm really curious to see how all of this connects back to the concept of cubical excision and the framework we developed in section 2, you know, with those excisable posets.
Right. So, good question. Let's explore that connection.
Okay.
So, they start with a key proposition. For a morphism WWV in fin T, the cube Re1 cat TV is a complementable parameterized poset.
Okay.
This might not be immediately obvious.
Yeah.
So let's break down why this is true.
Okay.
First, recall that the diagonal Functor of 1, it has both left and right adjoints.
Okay.
And this is because this one has finite coproducts and adjoints love to interact with colimits.
Right. Adjoints and colimits, a match made in category theory heaven.
Exactly. And so a handy lemma from Hilman's survey tells us that if a functor has both left and right adjoints, then applying a functor like Dotto to it preserves this property.
Okay.
So 1, Jo1, Dov1 also admits both left and right adjoints.
Okay, I'm following so far. We've used that lemma to show that 1 has both left and right adjoints. How does that tell us that 1, 1 is a complementable parameterized poset?
Right. So the existence of these adjoints implies the existence of finite coproducts in 1, 1.
Right, okay. So by showing that we has these adjoints, we've essentially shown that 1, 1 has the necessary coproducts. What about the other conditions like distributivity, complementability?
Right. So those follow quite naturally from the structure of these cubes. So ordinary cubes, think of the familiar three-dimensional cube. They're finite products of where 1 and cat.
Mm-hmm.
And crucially, they are distributive and complementable.
Right. I remember distributivity from our discussion of posets. The product and coproduct operations need to distribute over each other.
Exactly. And since Wend 1, they're fiber-wise cubes.
Sure. Okay.
Meaning they look like ordinary cubes when we, restrict them to different objects in T.
Okay.
We can deduce that Wend 1 is also distributive and complementable.
Gotcha.
And this follows from the fact that coproducts are, computed fiber-wise.
Okay, that makes sense. We're basically inheriting those nice properties from the ordinary cubes that make up these parameterized cubes.
Exactly, yeah.
Okay, so we've shown that these cubes are indeed complementable parametrized posets. What's the next step in connecting them to excisable posets?
Right, so now we need to equip them with an excisable poset structure.
Okay.
So remember, an excisable poset, it has this, distinguished downward closed subposet.
Mm-hmm.
So for a morphism WWEV in Fint, the full subcategories, W2 and W1, are downward closed.
Okay.
And this makes them perfect candidates for, defining excisable poset structures on Y1.
Okay, hold on. Let me process that. So the first inclusion, that is the punctured cube, right?
Right.
Like taking a cube and removing its top vertex.
Right.
And that's naturally downward closed because it excludes the final object.
Exactly, yeah.
But what about the second inclusion? W1. What does that represent?
Yeah, so that one represents the singleton inclusion we discussed earlier.
Okay.
The map, Tawa.
Okay.
And so the downward closure of this inclusion, it's not as, immediately obvious.
Right.
So we need a bit of a technical argument to prove it.
Okay, walk me through it.
Okay, so the proof involves considering a morphism in W.
Okay.
With a target in W.
Okay.
And we want to show that its source must also be in W.
Right.
So by strategically focusing on a specific case where T has a final object,
yeah,
and using the fact that singleton inclusions are stable under base change,
mm-hmm,
we can cleverly rephrase the problem.
Okay.
It becomes a lifting problem in a diagram involving Euro, Visure, 1, your...
A lifting problem.
Yeah.
So we're trying to find a map that sort of lifts a given map to a different part of the diagram.
Exactly.
Okay.
And thanks to the adjunction to W, this lifting problem is equivalent to another lifting problem.
Okay.
In a simpler diagram involving WW N, and error 1.
Okay.
So by carefully analyzing the structure of the map, W, we can show that the required lift exists.
Okay.
And this establishes the downward closure of W1.
Okay, that was a lot of category theory. But I appreciate how you broke it down.
Yeah, it's a bit technical.
Yeah.
But yeah.
So we've shown that both W1 and Area 1 are downward closed. What's the significance of that?
Right. So this means we have two ways to equip WR with an excisable poset structure, leading to two distinct types of excisable posets: the singleton W cube and the spherical W cube.
Okay, two flavors of excisable cubes. What sets them apart?
Right. So the singleton W cube, denoted as W1, W, focuses on the singleton inclusion map, W1.
Okay.
On the other hand, the spherical W cube, denoted as W1, 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 emphasizes the punctured cube, W1 work.
Okay, so the singleton cube is all about those singletons.
Right.
And then the spherical cube is about the punctured cube.
Exactly.
And based on these two types of cubes, we get two corresponding notions of excisiveness.
Right, exactly. We have singleton W excisiveness and spherical W excisiveness.
Okay.
So for morphism WWV in Fent and category C, D, Cat T with the necessary parameterized colimits, a functor FCD is singleton W excisive, or spherically W excisive if the morphism VF, VC, AV, and Cat TV is Bigsta excisive or sign excisive, respectively.
Okay, so we're essentially specializing our general notion of excisiveness to these cube-based excisable poset structures.
Exactly.
Okay. And then, so an important observation here is that a spherically quasi-excisive functor is automatically singleton re-excisive.
Right.
And that follows directly from the definition of excisiveness and the fact that the inclusion one factors through the inclusion rule at 1.
Exactly.
Okay, so spherical excisiveness is a stronger condition than singleton excisiveness.
Right.
Okay.
Yeah.
So let's shift gears a little bit and discuss how all of this connects to the concept of semiadditivity and stability.
Right.
Those were mentioned in the introduction, and I'm excited to see how they fit into the picture.
So recall that in, Goodwillie calculus, a reduced functor between pointed categories with finite coproducts is semi-additive if it's one excisive.
Right.
This means it preserves the zero object and sends push-out squares to pull-back squares. So in our parameterized setting, we can generalize this notion using W-excisive functors.
So we're taking the idea of semiadditivity from Goodwillie calculus and kind of like extending it to this more general setting using W-excisive functors. How does that work?
Right. So suppose T has a final object T.
Go.
And WWT is the unique map. Let C be a pointed category with finite indexed coproducts, and let Joe 1U. This is a singleton co-Cartesian diagram.
Okay.
Now consider a W-excisive functor FCED that preserves zero objects.
Okay.
So we can define two composite functors, W1, WWWC, X right to WC, C and WWWWC, X right to C.
Okay. So we have these two functors, up to U, both built from WW and the diagram on side. What do they represent intuitively?
Right. So these are our key players in understanding semiadditivity in this context.
Okay.
Let's break them down.
Okay.
So the functor up here represents a singleton co-Cartesian WQ.
Yep.
It's essentially, encoding a specific push-out diagram within the category C.
Okay, a push-out diagram. That sounds familiar.
Right. And then the functor barb, it represents a singleton Cartesian W cube.
Okay.
Encoding a specific pullback diagram.
Okay.
Within C.
Okay.
And these cubes, these satisfy the following.
Okay.
Wx at a 1 and UV above Ox and UV above a day. So these conditions tell us, how these cubes behave at their, corners.
So these cubes capture these very specific push-out and pullback diagrams. How are they connected?
Right. So the connection is established through this special transformation.
Okay.
Called the semiadditivity norm map.
Okay.
Denoted as ABI-AOAIC.
Okay, a norm map. That kind of reminds me of linear algebra, where the norm measures the size of a vector. So what does this semiadditivity norm map measure?
Right. So it measures the deviation of the functor f from being semi-additive. Okay. We define it using the norm transformation WWC, which exists internally to T. Okay. We set the transformation 1 x right ERS WWC AC,
Okay.
where the horizontal arrow is W, followed vertically by the norm transformation, then W.
Okay. So the semiadditivity norm map is kind of like a yardstick for how close our functor is to being semi-additive.
Right, exactly.
How do we actually use it to analyze the functor, though?
Right. So for any functor FCD, we get a canonical transformation phi x right element interchange of functors as U1
Okay. So we're applying f to both of our cubes, and then we're comparing the results using the norm map.
Exactly.
Okay.
And so here's a crucial property of Cartesian diagrams that comes into play.
Okay.
So suppose we have a natural transformation FGW1C between two Cartesian diagrams.
Okay.
Such that F1 is UG and S is SG, so for all maps, SUAT, that are not equivalences.
Okay.
Then F is naturally equivalent to G.
Okay. So this property is saying that if two Cartesian diagrams agree at their top corners and also agree when they're restricted to certain subcategories, then they must basically be the same diagram.
Right, exactly.
But I'm saying if two functions agree on a large enough set of points, then they must be the same function.
Right.
Yeah.
So this property allows us to compare and analyze diagrams by focusing on specific parts of them.
Right.
And it'll be crucial for the inductive arguments.
Okay.
That we'll use to prove the main results.
Okay, I'm ready for some inductive proofs. What's next?
Right. So before we dive into those proofs, we need to introduce some terminology.
Okay.
For atomic orbital categories that will make our lives easier.
Okay.
So we say an atomic orbital category, T has length N. If the longest chain of non-equivalent morphisms in T is of length N.
Okay.
And if T has length N for some finite N, then we say it has finite length.
So the length of an atomic orbital category is a measure of its complexity based on how many non-equivalent morphisms we can string together.
Exactly, yeah. And so a nice property is that if T has a final object in length 0,
okay,
then T is equivalent to the trivial category with just one object.
Okay.
And one morphism.
If there are no non-equivalent morphisms, then everything must collapse to a single point.
Exactly.
Okay.
Furthermore, for a non-equivalence morphism FU, W in T, the lengths of TU and TW, denoted U and EW respectively, satisfy U W1.
So the length of the slice category over U is strictly less than the length of the slice category over W.
Exactly.
Okay.
So this property will allow us to perform inductive arguments based on the lengths of these slice categories.
This will be useful for our inductive arguments.
Exactly. And now, building upon this notion of length, we can define a locally short atomic orbital category.
Yeah.
So an atomic orbital category, T is locally short if for every object VAT, the slice category TV has finite length.
Okay.
So this means that the partial order on 0 TV, defined by xy if and only if hom TV xyo, has finite length.
So in a locally short atomic orbital category, the relationships between the objects are like somewhat bounded,
right,
meaning that we don't have these infinitely long chains of morphisms between them.
Exactly. And this property simplifies many arguments.
Okay.
And allows us to utilize powerful inductive techniques.
Right.
And examples of locally short atomic orbital categories include the orbit category, OG of a finite group G.
Okay.
The category epid of finite sets and surjections up to size D, and the category vect AD of K vector spaces of dimension at most D, and surjections where K is a finite field.
Okay. So there are plenty of interesting categories that fall under this definition.
Yeah, exactly.
Okay, so now with these definitions in place, can we state the key lemma that connects singleton W excisiveness to semiadditivity?
Right. So suppose T is a locally short atomic orbital category.
Okay.
And let C and D be pointed T categories that are parameterized by complete.
Okay.
If a reduced functor, FCD, is singleton W excisive for all morphisms WWV in fin T,
okay,
then it is T semiadditive.
So it's kind of like bridging this abstract concept of singleton excisiveness with this more concrete property of semiadditivity.
Exactly.
How does the proof work?
Right. So the proof proceeds by induction
Okay.
on the length of the category T.
Okay.
And by replacing T with TV, we can assume without loss of generality that T has a final object and finite length, and W is a map to the final object.
Okay.
The base case of length Zell follows directly from observations 3.4.1 and 3.4.8.
Okay.
Which tell us that in this case, semiadditivity and singleton excisiveness coincide.
Okay, so the base case is pretty straightforward. What about the inductive step?
Right. So for the inductive step, we use the W excisiveness of F to show that the W cube fin, the W no DW C X right over W, C X right over F D is Cartesian.
Right. Fin encodes how F transforms the push-out diagram represented by Fx.
Exactly. Now, using observations 3.1.4 and 3.4.8 and induction on the lengths of the slice categories, we can establish that the norm map from equation 11 induces an equivalence between Fan and VFF when restricted to a one arming.
Okay, so we're using induction to show that these two diagrams are basically the same when restricted to this specific subcategory.
Exactly. And since F is always Cartesian by our earlier observations, and we've shown that Fan is Cartesian, by the W excisiveness of F, we can apply proposition 3.4.6 to conclude that FWW auto X WWFX is an equivalence.
Okay.
And this establishes the desired connection between singleton W excisiveness and T semiadditivity.
Great. So that completes the proof of the lemma.
Exactly.
Yeah. It was a very nice inductive argument. Right. I really appreciate how you highlighted the role of the locally short property in making that induction work.
It's crucial. Yeah.
All right, so we've got this key lemma connecting singleton excisiveness and semiadditivity. Where do we go from here? Right,
so now we're ready to call theorem 3.4.15, which connects spherical faithfulness to semiadditivity.
All right.
So it states that if T is a locally short atomic orbital category and C is a pointed T category that is parameterized by complete and spherically faithful, then C is T semiadditive.
So now we're finally seeing how spherical faithfulness relates to this more familiar concept of semiadditivity.
Exactly. So the proof involves demonstrating that the identity functor ICC, CC, is singleton W excisive for all morphisms W infinity.
Okay.
And once we've shown that, we can simply apply lemma 3.4.12 to conclude that C is T semiadditive.
Okay, so how do we show that the identity functor is singleton W excisive?
Right, so since C is W spherically faithful, the transformation itoi is an equivalence.
Okay.
So using the formula for pi from theorem 2.3.12 and remark 3.4.13, we can then deduce that ITC polyoEC is also an equivalence.
So we're using the spherical faithfulness of C to show that the identity functor is equivalent to its spherical W excisive approximation.
Exactly. And this equivalence implies that I80C is spherically W excisive.
Okay.
And by observation 3.3.5, spherical W excisiveness implies singleton W excisiveness.
So the identity functor is singleton W excisive for all W, and we can apply the lemma to conclude that C is T semiadditive. Beautiful. It's amazing how everything just fits together so perfectly.
Yeah, it's really neat.
Yeah.
And now we're finally ready for the grand finale, theorem 3.4.16.
I've been waiting for this. What does this grand finale tell us?
So theorem 3.4.16, it provides this beautiful and satisfying characterization of parametrized stability in terms of spherical invertibility. So it states that if T is a locally short atomic orbital category and C is a pointed parameterized presentable T, all right, so you send over this preprint paper, Parametrized Functor Calculus, Excision, Spheres, and Semiadditivity by Kaif, Hilman, and Stoll, Linskens. It's fresh off the press, dated October 30th, 2024.
Yeah.
And it promises to unpack some really, really cool mathematics, particularly building on Goodwillie's functor calculus.
It certainly does. Yeah, this paper really lays the foundation for some powerful new tools that could revolutionize how we think about homotopy theory and beyond, really.
So the paper focuses on revealing multiplicative structures within homotopy theory, but why is that so important?
You can think of it this way.
Okay.
In algebra, Understanding how polynomials behave under multiplication,
Right.
that's key to unlocking their deeper properties.
Mm-hmm.
Similarly, in homotopy theory, grasping these multiplicative structures is crucial for unraveling lots of mathematical mysteries.
Interesting analogy.
Mm.
And the authors are taking a unique approach here, using something called excisible posets. They even compare their approach to analyzing functions like x to the nth power to studying polynomials in algebra.
Exactly. Excisable posets provide a really structured way to break down these really complex mathematical objects into simpler pieces,
Okay.
making them easier to analyze. It's a powerful technique for uncovering these hidden relationships.
And they're using these tools to generalize the Wirth-Muller isomorphism, which, as you know, links representation spheres and orbits in equivariant homotopy theory.
Precisely. They're taking that classic concept and extending its reach
Mm-hmm.
into a broader, more abstract realm, hinting at potential connections to relatively new areas like atomic orbital categories.
Sounds pretty groundbreaking. Okay, let's walk through this paper page by page. Starting with the introduction on page 1. They dive straight into the significance of those multiplicative structures in homotopy theory, specifically calling out the subtleties related to norm functors in equivariant higher algebra.
Right, and they position their work within the existing literature, referencing Blumberg and Dotto's work on equivariant linearity.
They highlight the previous attempts at parametrized calculuses struggled with the complexity of these multiplicative structures, especially in the context of norm functors. But their approach using excisable posets offers a fresh perspective.
Exactly. Their method emphasizes clarity and efficiency, relying on the fundamental properties of posets, rather than complicated machinery.
Gotcha.
It's all about finding elegant and streamlined solutions.
Okay, on to page 2. Here we get a sneak peek at the structure of their framework. The table of contents highlights excisable posets, parametrized cubical excision, and an appendix providing a roadmap for our exploration.
And they introduce another intriguing concept, parametrized spheres.
Okay.
Generalizing the idea of regular representation spheres, which are foundational in classical equivariant homotopy theory.
Right.
They're essentially extending these ideas into a broader, more abstract setting.
And they hint that these results could lead to new insights into atomic orbital categories.
Absolutely.
A relatively recent development in mathematics.
It's fascinating how they're weaving together these diverse mathematical threads, showcasing the interconnected nature of mathematics.
Okay, let's move on to the heart of the matter, pages 7 through 12, where they define those excisable posets. They start by defining a complementable poset, a poset where every element has a unique complement.
Right, and they emphasize two key properties.
Okay.
Distributivity, ensuring that operations behave nicely, and complements, allowing for the decomposition of these structures in a specific way. You could almost think of it like a Boolean algebra, but for more abstract mathematical objects.
Oh, that's helpful. Then they introduce smashing supposits in construction 2.1.7, essentially focusing on a specific part of the poset while ignoring the rest.
Precisely. They call this smashing localization.
Okay.
Think of it as zooming in on a particular region of a mathematical space to analyze its properties in isolation.
They also highlight in Corollary 2.1.9 that these smashing localizations give rise to Bousfield localizations.
Exactly. They are showcasing the depth and interconnectedness of their approach,
Okay.
linking their constructs to existing concepts in homotopy theory.
Okay, now for the formal definition of an excisable poset
Yeah.
in definition 2.1.11, it's a complementable poset with a specific type of supposit one that's downward closed, meaning that if an element is in the supposit, all of its ancestors are too. They give a forward reference to the singleton inclusion map, which we'll see later.
Right. That singleton inclusion map provides a concrete example of how this abstract concept plays out in practice.
They then define Sco-Cartesian and Cartesian diagrams, essential tools for studying how functors behave when applied to specific types of diagrams. I assume these terms arise from viewing the functors as objects in a functor category.
You're absolutely right. They then meticulously establish several properties of these diagrams.
Okay.
For example, in Proposition 2.1.17 and Proposition 2.1.19, they demonstrate how specific operations preserve these crucial co-Cartesian and Cartesian properties.
So it's like they're creating a rule book for how to manipulate these diagrams without breaking them.
Precisely. They're laying the groundwork for rigorous proofs and ensuring their mathematical constructions are robust.
This is already getting fascinating. Okay, let's move on to pages 12 through 16, where they introduce face decompositions. They start by defining face posets and showing how to decompose a poset into these smaller pieces, analogous to dissecting a cube into its faces.
Right. They do this using triple decompositions, where a poset is split into 3 disjoint subsets.
Okay.
A famille dollars and sevels, whose union makes up the entire poset.
So each face poset, denoted as fio de, captures a specific combination of elements from the original poset.
Exactly. They then demonstrate, in construction 2.2.4, how this decomposition process preserves the excisable structure. It's like ensuring that the pieces of a puzzle still fit together after you break it apart.
Okay, I'm with you so far. Then they prove 2 crucial results in Proposition 2.2.5 and Proposition 2.2.7, highlighting how these decompositions preserve the co-Cartesian and Cartesian properties of diagrams.
Those propositions are essential. They demonstrate that if you have a diagram with those nice gluing properties,
Right.
breaking it down into its faces preserves those properties.
Okay.
And conversely, if all the faces of a diagram have those properties, the whole diagram does too.
It's like having a mathematical guarantee that you can analyze a complex structure by understanding its individual components.
Exactly. It's a powerful technique. Okay, let's move on to the concept of excision itself. On pages 16 through 21, they formally define successive functors in definition 2.3.1.
These are functors that map those special co-Cartesian diagrams to Cartesian ones.
Precisely. They emphasize that this notion of excision remains valid even when you change your perspective.
Okay.
It's stable under base change.
Mm-hmm.
This robustness ensures that their concept is well-defined and not just a quirk of a particular viewpoint.
They then introduce differentiability in definition 2.3.4, capturing the idea of functors changing smoothly, akin to the concept of differentiability in calculus.
Right. And this concept of differentiability plays a crucial role in their main result of this section. Theorem A. This theorem provides a way to construct excisive approximations of functors, simplified versions that capture their essential behavior.
Okay, let's break down this theorem. First, they introduce the pre-excisive approximation functor in construction 2.3.5, which acts as a stepping stone towards their ultimate goal.
Yes, and they prove several lemmas. Lemma 2.3.6 through lemma 2.3.11a.
Okay.
Establishing key properties of Tigma. They show, for instance, that it preserves properties like Sleft-Can extensions and final objects.
It's like they're meticulously checking each step to ensure the construction is sound and well-behaved.
Exactly. Then, building on this foundation, they define the crucial excisive approximation functor, denoted as sigma, in construction 2.3.8. This canassa is the tool they'll use to simplify complex functors while retaining those essential excisive properties.
So PCMA acts like a mathematical filter,
Precisely.
removing unnecessary complexity and revealing the core structure of the functor.
And they demonstrate its effectiveness in lemma 2.3.0,
Okay.
proving that those Goodwillie approximations are excisive, meaning that when people is applied to a functor,
Right.
the resulting functor satisfies the desired excisive properties.
They then prove in lemma 2.3.11 that these Goodwillie approximations are idempotent. This implies that applying Peterma twice yields the same result as applying it once, ensuring a clean and efficient approximation.
Absolutely. It's all about elegance and precision in their construction.
Yeah.
Finally, all their efforts culminate in Theorem A,
Okay.
the excisive boost field localization theorem.
What exactly does this theorem tell us?
It formally establishes that Pisma is the best possible way to approximate a functor,
Right.
while preserving those excisive properties. Think of it as finding the most efficient and elegant solution to a complex mathematical puzzle.
Wow. So they've not only constructed a tool for simplifying functors,
Right.
but also proven its optimality.
Exactly.
This is pretty groundbreaking, isn't it?
It certainly is, and it's just the beginning.
Okay.
This theorem lays the foundation for everything that follows,
Right.
including their exploration of parametrized cubical excision.
Okay.
Are you ready to move on to page 21 and dive into those cubes?
Absolutely. Let's unpack those cubes.
All right, so on page 21, they introduce the concept of a parametrized cube, defined as an indexed product of the category delta 1301.
Okay, so they're taking that familiar notion of a cube from geometry and extending it to this more abstract categorical setting.
Exactly. And remember, they're working within the framework of atomic orbital categories,
Right.
which have those special properties that make these cubes particularly well-behaved.
Right, those well-behaved categories we discussed earlier. So they're not working with just any random categories they've chosen, a setting where these cubes will interact nicely with the other concepts they're building.
Precisely. They then point out a key feature of these parametrized cubes. The only global points they have are the initial and final objects, denoted as empty set and $1 respectively.
Interesting. So within these abstract cubes, only the starting point and the ending point are considered global. I'm curious to see how this plays out later on.
Yeah, it's a subtle but crucial observation that will be important for their later arguments. They then remind us, in fact, 3.1.5, that these parametrized cubes, despite their abstract nature, are actually posets. They reference their earlier work in Hill 24a to support this.
So those cubes we've been visualizing actually fit neatly into the framework of posets that we've been building up. It's all starting to connect.
Exactly. They're carefully weaving together these different mathematical structures to create a cohesive and powerful framework. Now let's move on to construction 3.1.7, where they introduce the singleton inclusion map, denoted as phi euro, W triangle left right, a WW delta phi or.
Okay, back to those singletons. This map is all about isolating those individual elements within a cube, right?
Precisely. Think of it as a filter that only lets those individual elements pass through. And they emphasize, once again, that this singleton inclusion map is stable under base change.
So, just like with excision, we can be confident that this concept is robust and holds true regardless of our perspective. They then delve into some technical details about this singleton inclusion map, proving two important results, in fact, 3.1.9.
Right. First, they show that the singleton inclusion map is fully faithful. This means it preserves the relationships between objects.
Right.
It's like creating a perfect replica of those individual elements within a different context.
Okay. So it's not just filtering out those individual elements, it's also preserving their relationships with each other. That makes sense.
Exactly. And second, they establish a connection between singleton inclusion maps and indexed products, highlighting how these maps interact with the way we combine objects in this categorical world.
Okay, I'm seeing how they're meticulously building up a framework here, carefully defining each piece and establishing its key properties. Now let's move on to those singleton co-Cartesian and singleton Cartesian cubes.
On page 25, they define these special types of cubes that are constructed using those singleton inclusion maps. Think of them as cubes built up from those individual building blocks, those singletons, in a specific way.
So it's about understanding how those individual elements come together to form a larger, more complex structure.
Precisely. And they prove a crucial result in proposition 3.1.14. Showing that the external index product of a singleton co-Cartesian cube is, again, singleton co-Cartesian.
So if you combine these special cubes in a specific way, they retain that key property of being built up from those individual elements. It's like ensuring that those building blocks stay distinct even after you've assembled the structure.
A great analogy. This proposition provides a mathematical guarantee that those individual elements don't lose their identity when you combine the cubes. Now we've laid a solid foundation with those parametrized cubes and singleton inclusion maps. Let's move on to page 27 and see how they use these tools to construct suspensions and spheres. This is where things start to get really exciting.
Okay, I'm on the edge of my seat.
Yeah.
Tell me more about those parametrized spheres.
Well, they begin by defining the parametrized suspension, which is a specific way of suspending an object in a category. Intuitively, this means adding a dimension to it. But in this abstract categorical sense.
Adding a dimension, that sounds almost geometrical.
It is. It's fascinating how they're bringing geometric intuition into this abstract world. They then introduce the parametrized loop functor, which is essentially the inverse of the suspension functor.
So you have these two functors, suspension and loop, that are kind of like opposites in this mathematical world.
Right.
And then using these tools, they define the parametrized sphere.
Right. It's the heart of this section. They define the parametrized sphere as the suspension of Ohlers. Which is the simplest possible sphere consisting of just 2 points. They denote this parametrized sphere as zero-Lollers, where Dollars is a morphism in the category. So they're taking that basic building block, Severs-Zollers, and suspending it to create these more complex parametrized spheres. And they point out that zero-Zollers can represent spheres of various dimensions depending on the context. Exactly. They found a way to capture the essence of a sphere in this general abstract setting, and they prove a crucial result in proposition 3.2.3.
Okay.
There's an adjunction between those suspension and loop functors.
Okay, back to those adjunctions. Remind me, what does an adjunction signify?
It represents a kind of duality between two functors. They're opposite, but also connected in a specific way.
Okay.
It's a powerful concept in category theory that lets us relate seemingly different structures. They then introduce two key concepts: spherical faithfulness and spherical invertibility.
Okay, let's unpack those terms. They sound pretty important.
They are. Spherical faithfulness essentially means that the suspension functor behaves nicely. It preserves the relationships between objects.
Okay.
Spherical invertibility is even stronger. It means the suspension functor is an equivalence, meaning it's reversible.
Okay. So spherical faithfulness is a desirable property, and spherical invertibility is even better. They give a specific example relating to the orbit category $02 of a finite group in example 3.2.5 to illustrate these concepts.
Right. That example shows how these abstract concepts manifest in a more concrete setting,
Right.
helping us to grasp their significance. And then in example 3.2.6, they make a fascinating observation. If the parametrized sphere 6-baller is invertible in a certain category, then that category itself becomes spherically invertible.
Wait, so if that special sphere has an inverse, it somehow makes the whole category invertible. What does that even mean in this context?
Think of it like this. Invertibility, in this case, means there's another object that can cancel out sigus when you combine them.
Right.
Much like positive and negative numbers adding up to 0. If sigus this inverse in a category, it implies a certain symmetry and reversibility within that category, leading to that spherical invertibility.
Okay, I think I'm starting to grasp the implications here. It's amazing how such a seemingly simple concept like a sphere can have such profound consequences for the structure of an entire category.
It really highlights the elegance and power of abstract mathematics.
Yeah.
They then establish a calculus for manipulating those spheres in proposition 3.2.7, proving 3 key relationships.
So they're giving us the tools to work with these parametrized spheres.
Exactly.
Rules for how they combine and interact with each other.
Exactly. These relationships will be crucial for their later arguments, allowing them to manipulate those spheres with precision. Okay, we've explored those parametrized spheres and their properties. Now it's time to connect them back to the earlier concept of excisable posets. Let's turn to page 30.
Right, back to those excisable posets. I'm curious to see how they tie everything together.
On page 30, they begin to bridge the gap, showing how those parametrized cubes we've been discussing fit neatly into the framework of excisable posets.
So those cubes, despite their geometric origins, actually possess the structure of excisable posets. It seems like everything is starting to connect beautifully.
It is. It's a testament to the deep interconnectedness of mathematical concepts.
Yeah.
They prove this connection formally in Lemma 3.3.1 and Proposition 3.3.2.
Okay.
Establishing that those parametrized cubes are indeed complementable posets, and that certain subcategories provide excisable structures.
So they're showing that those cube posets satisfy all the requirements we laid out earlier for excisable posets. It's like a perfect fit.
Exactly. It's a satisfying moment when seemingly different concepts harmonize so well. They then link these cubical structures to the earlier ideas of singleton and spherical excision.
Right, those concepts that describe how functors behave when applied to specific types of diagrams.
Precisely. In definition 3.3.4, they introduce singleton-Dallal excisive and spherically Dollar excisive functors. These definitions capture how functors interact with diagrams, built from those individual elements and those parametrized spheres, respectively.
So it's about understanding how functors behave when you throw those individual elements and those spheres at them. It's almost like testing how robust those functors are.
That's a great way to think about it. And in observation 3.3.5, they point out that any functor that's spherically excessive is automatically also singleton excisive.
So if a functor passes the spherical test, it automatically passes the singleton test. That's handy. It's like getting a 2-for-1 deal.
Precisely. It simplifies their analysis and highlights a hierarchy within these concepts.
Okay.
And with that, we arrive at the final chapter of our mathematical journey: semiadditivity and stability.
Okay.
On page 32, they bring all these pieces together, culminating in their final 2 main theorems.
Right.
Take a deep breath. Are you ready for this?
I am. Let's dive into those theorems. Okay, so page 37, appendix time. It's easy to skip over these technical sections, but I have a feeling there are hidden gems in here
Oh, absolutely.
that make those main theorems possible.
You're absolutely right. The appendix might seem like a technical aside, but it provides the essential machinery
Okay.
that underpins the main results. They start by defining the co-Cartesian unstraightening of a functor
Okay.
in definition A1.
Okay, unstraightening, that's a new one. What are the unstraightening exactly?
So imagine a functor as a map that takes objects from one category and places them into another category.
Okay.
This unstraightening process essentially reverses that mapping. It takes those placed objects and unstraightens them back into a diagram
Okay.
within the original category.
So it's like taking a tangled up ball of yarn and carefully unwinding it, revealing the original strands and how they were connected.
Exactly. And they use this unstraightening process to define the lax limit of a diagram in definition 8.2.
A lax limit. Interesting. What makes it lax?
A lax limit is a way of combining objects from different categories into a single object, but with more flexibility than a traditional limit.
Okay.
Think of it as finding a common ground between different objects while allowing for some wiggle room.
Ah, so it's a more flexible way of finding a consensus between different mathematical objects.
Precisely.
Okay.
They then prove a key result in lemma 8.5. If the functors in a diagram are all left adjoints,
Okay.
then the lax limit of that diagram also has a right adjoint.
Right adjoints. Those dual concepts we discussed earlier.
Right.
So if the individual functors have this special dual relationship, the combined object inherits a similar relationship. It's all about preserving structure, even when you're combining things.
Exactly. It's a beautiful example of how the abstract machinery of category theory can illuminate deep connections between mathematical objects.
It really is.
And that brings us to the main result of the appendix. Theorem 8.6.
Okay, what does Theorem 8.6 tell us? It feels like the culmination of all this technical groundwork.
Theorem 8.6 provides a powerful tool for decomposing the right adjoint to a limit into simpler pieces.
Okay.
It's like taking a complex machine and carefully disassembling it, revealing how each component contributes to the overall functionality.
So it's a way of breaking down complexity to understand the underlying mechanics.
Precisely. And they apply this theorem to a specific case, obtaining corollary 8.7, which provides a way to decompose colimits into simpler pieces.
Colimits, those ways of combining objects in category theory.
Yeah.
So they're giving us a toolkit to take those colimits apart and analyze their building blocks.
Exactly.
Wow, what a journey. We've gone from the abstract foundations of excisable posets to the concrete implications for semiadditivity and stability, with a crucial detour through the technical machinery of the appendix.
It's been a true deep dive,
It has.
exploring not just the results, but the underlying machinery that makes those results possible.
Absolutely. We've explored those three powerful theorems, learned how to construct excisive approximations of functors, delved into the world of parametrized spheres, and uncovered hidden connections between seemingly disparate concepts like spherical faithfulness and T-semiadditivity.
And we've seen how the authors, through rigorous definitions, lemmas, propositions, and theorems, have built a powerful and elegant framework for understanding complex mathematical structures.
This paper truly showcases the beauty and power of abstract mathematics and the importance of carefully laying the groundwork to achieve those breakthroughs.
I couldn't agree more. This paper is a testament to the ingenuity and deep insights of Hilman and Linskens. It's exciting to imagine the impact this work will have on the field of mathematics.
So to our listener out there, we hope you've enjoyed this deep dive into the fascinating world of parametrized functor calculus. We encourage you to explore this paper further and consider the potential applications and connections to your own areas of research. Until next time, keep exploring, keep questioning, and keep diving deep.